Madam, please unmute, madam.
Sir, participants are joining, sir.
Okay.
Faculty team is following up.
Sir, very good morning, sir.
Good morning, everyone.
Good morning.
Okay.
Madam,
Sir, sir is
Yeah.
having some issue in the link, so he's joining via mobile, sir.
yeah, you can send it to his mobile, madam, through
Yes, sir.
WhatsApp.
Yes, sir. Yes, sir.
You can join.
He's asking us for 2 minutes, sir.
Yeah, no problem.
We'll wait for another couple of minutes. Yes, sir.
Please, sir. Sorry, sir, Mr. Maharajan, sir. They're waiting for Dr.
I
Pratap.
know. When things are happening online,
Yes,
these
sir.
things are bound to happen. I can understand. No issues. But generally, what happens is, say, when we, develop products and when the senior management is around, and when we, and all that time, it used to work fine. We will do multiple rounds of testing. Everything works fine.
Correct.
The moment the senior leadership comes to our desk, when we start showing the demonstration, all of a sudden it stops working.
Yes, sir.
So it's I mean, that's how it is. And then, later we have to see what went wrong and then do the demonstration again. So this is not,
Correct, sir.
these are
Exactly, sir. We had a rehearsal yesterday evening. The link was working very fine. We had a complete
Yeah.
rehearsal with our faculty team. I don't know, some technical issue with Professor Desai, sir. He's connecting via mobile, sir.
Oh, sure.
Madam, recording started, madam, or yet to start?
The recording started, sir. So Professor is joining now, sir. Welcome, Dr. Pratap Singh Desai, sir. Welcome, sir. Principal, sir, you're on mute, sir.
Am I
Good
audible
morning,
now?
sir. President, sir, good morning.
Good morning.
Ji, good morning. Welcome.
Good morning.
Morning.
Good morning, sir.
Good morning. Sorry, there was some technical issue on my side.
No issues, sir. No issues.
Shall I start, sir?
Please, madam.
Good morning to all the distinguished dignitaries, respected guests, esteemed faculty members, and dear participants. It gives me immense pleasure to welcome you all to the inaugural function of the ISTE-BNY Knowledge Enhancement Program, 6-day faculty development program on quantum-assisted federated learning for secure distributed intelligence, organized by RMK Engineering College. On behalf of the management, faculty, and organizing team, I extend a warm and hearty welcome to everyone present here today. RMK Engineering College, an autonomous institution, has always been committed to academic excellence, innovation, and research-driven education. This FDP is yet another step towards empowering faculty members with emerging technologies and advanced knowledge. It is my proud privilege to express our heartfelt gratitude to the Indian Society for Technical Education for their generous support. We sincerely thank Dr. Pratap Singh Desai, President of ISTE, for sanctioning a grant of Rs 1.25 lakh for organizing this faculty development program. This valuable financial support has significantly contributed to the successful planning and execution of this program. It reflects IST's strong commitment towards enhancing the quality of technical education and empowering faculty members with emerging knowledge and skills. Sir, your encouragement and leadership continue to inspire institutions like ours to undertake impactful academic initiatives. We express our deepest appreciation for your kind support, sir. To formally welcome the gathering and present the institution profile, may I now invite Dr. K.M. Muhammad Junai, Principal, RMK Engineering College, to deliver the welcome address. Please, sir.
Thank you, madam. The most respected chief guest of today's inaugural function of ISTE-BNY Knowledge Enhancement Program. It's a 6-day faculty development program organized by RMK Engineering College, Information Technology Department on quantum-assisted federated learning for secure distributed intelligence. Chief guest, Dr. Pratap Singh Kakaso Desai, President of Indian Society for Technical Education, New Delhi, and guest of honor, Mr. Maharajan Muthuswamy, Director, BNY. On behalf of our respected chairman, sir, all the members of the management, faculty members, students, and my own behalf, I wholeheartedly thank ISTE and BNY for accepting our application to conduct this 6-day faculty development program under ISTE-BNY Knowledge Enhancement Program series organized by ISTE New Delhi. So thank you, sirs, Dr. Pratap Singh Kakose Desai, sir, and Mr. Maharajan Muthuswamy, sir, and also welcome you, sir. And I would like to welcome all the participants across the country for registering and started attending this 6-day faculty development program. On behalf of all of us, our best wishes to each and every one of you for your knowledge enrichment during this 6 days organized by IT department of our college. I also would like to welcome all the faculty members, HODs, deans, and principals of RMK group of engineering colleges, and also the management members, advisors of RMK group of institutions for this inaugural function. Welcome you all on behalf of all of us. Our thanks to each and every one of you for joining this inaugural function of ISTE-BNY Knowledge Enhancement Program. Regarding our institution profile, our RMK Engineering College, established in 1995, 31 years of excellence in providing technical education across the country. And our institution is affiliated to Anna University and received the autonomous status from UGC and Anna University during the year 2020. And in NIRF ranking, our institution is in the 150 to 200 band for the past 5 years. We have 11 UG programs, 3 PG programs, and all the departments are recognized as the center under Anna University to pursue PhD. More than 150 candidates are pursuing part-time PhD. And there are 240 plus faculty members. Out of that, more than 50% of faculty members have completed their PhD. And we have been maintaining 1:17 student faculty ratio, and there are 17 Center of Excellence laboratories in collaboration with knowledge partner industries in various latest technology domains for providing domain-specific hiring for all the students of RMK Engineering College. And every year, more than 85% of students are getting placement, including 30% of students getting paid or unpaid internship in various reputed industries. And our academic curriculum specialty is getting more than 40% of syllabus and curriculum content for all the departments from our knowledge partner industries. With respect to the research initiatives, so we have more than 600 papers every year published by our faculty members in reputed journals, and more than 2.5 crores worth of grants received from various funding agencies, including MSME, DST, and AICTE. And with respect to the entrepreneurship culture created inside the campus, we received 4-star status from Institution Innovation Council, Ministry of Education, Government of India, and more than 200 patents published and 41 patents granted by our students in the name of RMK Engineering College. So I sincerely welcome all the participants and also the chief guest and guest of honor to visit our institution for providing your valuable suggestions for further improvement and also for any kind of collaborative activity with respect to the research and innovation. So thank you for the given opportunity. I hope all the participants will enrich their knowledge with respect to this particular topic, quantum assisted federated learning for secure distributed intelligence, sponsored by ISTE-BNY under knowledge enhancement program. So thank you and welcome you all.
Thank you, sir. Thank you so much. Now let me introduce the distinguished dignitaries present with us today. Our guest of honor, it's now my privilege to invite our guest of honor, Mr. Maharajan Muthuswamy, Director BNY. And let me introduce him to you. He is a man of visionary with over 24 years of experience in application development, architecture, and technology leadership within the financial services industry. Mr. Maharajan brings a strong track record of driving large-scale business transformation through the strategic application of advanced technologies, including Java, Spring Boot, mobile application development, cloud computing, and infrastructure management. He is deeply committed to innovation and is known for tackling complex challenges head-on. Notably, he has also had the opportunity to develop cutting-edge solutions leveraging VR and AR technologies. Beyond his technical leadership, Mr. Maharajan is passionate about mentoring campus graduates and mid-level managers, finding genuine fulfillment in helping them grow and succeed in their careers. He is also recognized as one of the most sought-after technical interviewers at BNY, valued for his depth of expertise, high standards, and ability to identify strong technical talent. May I now invite our guest of honor, Mr. Maharajan Muthuswamy, Director BNY, to address the gathering. Please, sir.
Thank you, ma'am, and thank you, Principal Sir. And first of all, thanks for this opportunity to meet with all of you. And this is not my first stint with RMK because I've been associated with RMK way back from the year 2015, I believe. And we have done at least in my journey of first of its kind kind of work. I've done many of these first of its kind kind of work, and one such was the crowdsourced mobile application development, which was done with the help of third and fourth year students from RMK Engineering College way back in the year 2015. So I just wanted to quote that because that's the first ever stint I had with RMK, and I'm really proud to say that with minimal help from our side, RMK engineering students were able to develop that application within a week's time, and it was very powerful, and we are still using that application. So just wanted to quote that here. So thanks, thanks for that. And then when we talk about ISTE, I know we have Mr. Pratap here. So here, I'm associated with, from BNY, and I work with Vidya ma'am, and I'm one of the panelists, along with two other panelists, working with Vidya ma'am. And I'm proud to say that, year on year, we try to see how we can bring in more value, for, towards this program, because it is not just, with respect to, coming up with a curriculum or, understanding of curriculum or, doing the, sponsorship. We also are involved, deep into this program to ensure that, it's more of a train the trainer kind of a, activity that we are involved in, right? So we, typically are, looking into, bring the talent up, throughout India, not just, southern part of India or, northern part of India. So throughout India, wherever we have association, with the colleges and, with the help of ISTE. Even in the past years, we have delivered, many powerful programs, and I'm glad that, this program is taking off today, and there is more to come. And, especially for the faculties who are attending this program, the 6-day program, I'm 100% sure, you will see the value, towards the end of this program as to, what, at least, you can definitely take a lot of, new learnings from this, whole program, I believe, right? So that's the way in which, the program has been structured. So with that, I would like to, touch upon, couple of things. One with respect to what is happening in the industry, and second, why this train the trainer kind of a program is really required. So with the past 25 plus years of experience, what I have seen in the industry, what is happening in the industry is, say, we used to call it as waves, technical waves. And the way in which I started my career as a C and C++ programmer. So right now, when I look back 25 years back, how I started and where I am is completely different, right? Say, in the sense, the kind of technology stack, the kind of knowledge that was expected, way back in the year 1998, 2000. Now it's not the case. Now, we have, sophisticated tools that can generate code. But right now, the expectations in the, from the industry is completely different, right? So why, things are changing. So now, after the introduction of chat gpt, let me quote that chat gpt here, because see, even prior to that, we had or we have been doing a lot of work or research around artificial intelligence and machine learning. But when this entire technology was made available for the common man to use, so that is when people started seeing the power of AI and ML. And I would I can probably say that, the power of AI and ML was felt by the common man only around the time when ChatGPT was, introduced to the world. So I would say that's a breakthrough. So right now, what we are seeing is after that, there's a lot of improvements happening, a lot of changes happening, in the way how technology is improving, number one, and number two, how we are looking at job roles, and what is really expected of the graduates who are joining us, joining the industry, and how they are expected to be prepared for the job market. So how is that expected to happen? Obviously, mentors and faculties like you should also pay attention to what is needed in the market, and then bring the students up to that level to see how they are how they can be made marketable in the job industry, right? So job market. So with that, so what is happening here in this current world and the current situation? Say, gone are those days where we used to have requirements document, and then we do a design, and then after the design, we expect the coders to write application code, and then test, debug and deployments. All that is all gone. So right now, what is happening is all these things are being done by specific code generation tools, automation testing tools. So for anything and everything, we have tools. And what is needed from the students, or what is needed from the analysts or the programmers who are joining us? So first of all, first things first, the basic understanding of programming is always required. So there is no exception to that. So anybody who is good at programming will be able to sustain in this market. So that essentially means whatever we are learning through the curriculum is very much needed. But the applicability of the knowledge, right? Say, um, like last year, whatever that took 1 week for us to develop an application, today we are able to develop that application in a couple of hours using the code generation tools, right? So day in and day out, new AI tools are coming, and we have specific statistics saying with every in every 90 hours we are seeing new LLM models coming up, right? See, we are seeing in every 90 hours we are seeing new LLM models coming up. So that's the power of artificial intelligence we are talking about. So that said, how are we keeping ourselves up up to the expectations from the market? That will play a major role in terms of how we are relevant in the market, plus how we can make the students market ready. So given with all of these things that is happening around us, it is very essential for us to understand that not just artificial intelligence. So initially when I said wave, so we had different technology waves, and somewhere in the middle we had C and C++ applications, or got converted to Java and Spring Boot, and then people started talking about React, and Node.js and whatnot. And today, folks, especially the students, from the engineering community, they have this code word called MER and MERN, right? Say MERN stack. So which has been the trend all this time. But what is happening, what has been happening in the last, since the last 1 year, is there's a big shift in the paradigm, and how we are looking at market is, don't just focus on programming, focus on how you are able to decipher what is coming out from the code generation tools, right? If it is really good code or bad code, or is it applicable for the given requirement? So that's the kind of analytical skills that is required from the students, from the people who are facing the market. So this is where, as faculties, you will be able to make a big difference in the life of the engineering graduates who are expected to face the market after they are completing their course of engineering by 4th year. So with that, maybe I'll hand it over back to Sharon ma'am, and if anything else that I can help with, please let me know. I'll be around for some time. Thank you.
Thank you, sir. Thank you for your enlightening address. Thank you so much. Now let me introduce our chief guest of today's function, Dr. Pratap Singh Kakaso Desai, President of ISTE. Dr. Pratap Singh Kakasahib Desai completed his PhD from Shivaji University, Kolhapur. He has completed master's degree in mechanical engineering and master of business administration. He is the son of Shri Krantiveer Kakasahib Desai, the most sought freedom fighter. The Desai family rendered 5 freedom fighters to nation, and he was raised with strong values and principles. He has a prominent background of social reforms, patriotism, and education. Dr. P.K. Desai is working on design and development of femur bone prosthesis research. He delivered keynote addresses in India and abroad in conferences. Especially his deliberation on opulent Indian education and its history is highly revered. He has numerous national and international research papers to his credit. Dr. P.K. Desai has actively participated as member of All India Federation for Polytechnic Teachers Association. During his tenure in various organizations, he was instrumental in advocating the issue of granting pay band 4 to all engineering and polytechnic colleges. Currently, he is working on salaries to be paid by state government to self-finance engineering institutes. He is a member of various committees and task teams constituted by Government of Maharashtra. Dr. P.K. Desai attended and participated as member of Indian delegation on various international meets such as World Engineering Education Forum, International Federation of Engineering Education Societies, Global Engineering Deans Council in countries like US, Canada, England, France, Germany, Argentina, Brazil, China, Japan, Dubai, Australia, and Korea. Dr. P.K. Desai is the youngest ever president of the prestigious organization IST New Delhi, past vice president of IST New Delhi, IST Executive Council member for 2 terms. Is member representing India in Global Deans Council. Is chairman Indian Engineering Deans Council. Is member of Governing Council Engineering Staff College of India. Is a council member of All India Council for Technical Education. Is member of the advisory committee for the overall curriculum development cell IIT New Delhi. Is member of State Steering Committee of Technical Education of Government of Uttar Pradesh as well as Assam State. Is convener Maharashtra State Technical Teachers Association. He has been invited by Africa Asia Scholars Global Network, England, signatory to United Nations Global Compact, and member of European Alliance for Innovation. He also delivered keynote address at a joint program of Kent University, University of Greenwich, University of Creative Arts and Christchurch, hosted by AASGON in December 2016. He has been invited to deliver special address at University of Amber, Ethiopia. He visited almost 35 prominent universities in the world to study a technical education scenario in the world. He addressed conference on diversity in technical education at Chicago, US. He visited more than 45 countries to study the technical education scenario around the globe. Now, we are truly honored to invite Dr. Pratap Singh Kakaso Desai, President of IST New Delhi, to deliver the inaugural address. Please, sir.
Honorable guest of honor of today's inaugural function of 1 week FDP, which has been funded by BNY, Honorable Maharajan Muthuswamy, my colleague in the National Executive Council of ISTE, and the principal of this esteemed institution, Professor Dr. Junaid, Madam Shireen, other dignitaries present over here, my dear colleagues in the faculty, ladies and gentlemen. Let me make use of this opportunity to thank the organizers for inviting me over here to inaugurate this 1 week FDP at this pleasant morning, and provide me an opportunity to interact with you all. Friends, I'm not going to take much of your time. I'm just yesterday I was traveling from Mumbai to Kolhapur, and I was just going through an article written by Honorable Prime Minister regarding his vision of making India a Vikasit Bharat, developed nation by 2047. When it came to my mind, when we talk about the Vikasit Bharat, when we talk about the developed nation, then there are certain parameters which we have to take into consideration. Number one is the economic development of the country. Number two is the healthcare system. Number three is the education. Number four is the technology and research and innovation. These are the few very important parameters. And while just correlating the things, one example stuck to my mind, and that was of the Israel. Now you may say, why Israel? Is there because it's in the war affairs, involved in the war affairs? No. Israel was no more a country before 1948. What happened at that time, the Jewish people were not having their homeland, and there was a constant demand from the Jewish community that they should have their own motherland, own country. And after the Holocaust, the cruel Holocaust after World War II, there was a wave of sympathy in favor of the Jewish people, and United Nations declared separate Jewish land, that is Israel country, in the Palestine land. So I remember it's 10th May of 1948, and the 12th May the war broke between Palestine and the newly found Iraq. So this 2-day-old country has to face the war, and since then continuously they are involved in the war. So it's a completely desert. All conditions are adverse. Only thing is the commitment of the population to build a nation. Their dedication and their commitment, their perseverance, their passion made this country. Today, it has created a history. So why? Because we became independent. We were a country thousands of years back. We have a history of many thousands of years. Israel formed in 1948. Today, when we compare, as far as the economy per capita GDP is concerned, for us, for India, it's 2,800, 2,700 to 2,800 US dollars, and that of the Iraq is 66,000 US dollars. So that's a huge difference. Not only about the per capita GDP. When we come to the innovation index, it's in first 5 countries in the world. We are struggling to find the number in first 50. We were 180 few years back. Now I learned that it's between 40 to 50. When it comes to the power consumption, because electrical power consumption, per capita power consumption is an indicator of the development of any nation. So for India, we consume 700 to 800 kilowatts of the power per capita. That power consumption in Iraq is 6,500 kilowatts per capita. So that's a huge difference. Cloth consumption, we consume 6 to 8 kg of the cloth. Israel consumes 25 times more than us. So when it comes to the education, so we are just at the expanding stage, and again it's a unequal thing what we are dealing with. It's a world-class education they are delivering. Agriculture productivity, they are in the top 5 in the world. We are struggling to find a place in top 70 in the world. So that is what is the difference, and we are thinking, if at all we want to be a Vikasit Bharat, we have to take some inspiration from the country like Israel. Not only Israel, Israel is just because it has started in 1948. I gave the example of Israel. There are many examples like Dubai, Singapore. Of course, they are small countries. They have their problems are different. Our problems are different. But still, we have a country with a legacy. We have an established country. Once upon a time, we were called a golden sparrow. Entire world was looking at us. They were coming here, and that was just because of the educational development we achieved at that time, thousands of years back. So we all know about the Nalanda, Takshashila, Ratnagiri, all those universities. So our universities, history says that they were burned in 1000 years after General era. And first university, the oldest university of the world today, has started 100 years after that. So our history was far, far older and ancient. When I remember, I came across a grantha, that is a Susrut Sanhita. It's still available. It's compiled by a Dr. Susrut Sengupta. He was a known physician in 650 years before Christ, before General era. He conducted the first cataract surgery. He conducted the first brain surgery. He innovated the technique of doing a plastic surgery using a rhino skin. That was the term used for that was a rhinoplasty. So that was the technology developed at that time. Coming after that, we all know about the Chandragupta Maurya's period and Arya Chanakya. Arya Chanakya is known for his political strategies that has been wrongly being interpreted. He was a great visionary. For the first time in the history of the world, he talked about the responsible mining. The Director General of a mining, the post was incepted in the history of the world for the first time in the Chandragupta Maurya's regime 450 years before General era. He talked about the environment. He talked about the alloying technique and all. A systematic extraction procedure of the different metals. It's there written in the Kautilya's Arthashastra. The book is written by Chanakya, but it's not on the Arthashastra. It covers 14 different branches. So that was the level of the technology. Coming ahead, we all know about the Aryabhatta. We again wrongly interpret him as a mathematician because he gifted a magical figure of 0 to the world's mathematics. Actually, he was an astrophysicist, and his daughter Leelavati was a mathematician. She died early. In her memory, he studied mathematics, and in that study, he found the figure. He invented the magical figure of 0. So that was our contribution to the world's mathematics. This continued till, so whenever I come to Tamil Nadu, I see the magnificent temples of the Tamil Nadu and think of the level of the architecture at that time, because all those temples are thousands of years old. So that was the technology. Somehow we lost it. Maybe the more loss has been done in the British period, and because their intention was different. Their intention was to break the education system of this country, because unless somebody, Lord Macaulay, when he was sent to India, while addressing the British Parliament, he said that it's almost impossible to conquer this country unless we break its ancient education system. And they did it. And they introduced the Macaulay's education policy, which aimed at producing clerks, which aimed at following the orders, which aimed at following the instructions. And therefore, unfortunately, we are using the same technique till today. And even that too in engineering also, and therefore we are not producing the engineers. We are producing engineering clerks. So no earth-shaking research is coming from this country. So I guess it doesn't mean that we have done nothing. We have done many things, but that's not sufficient. We have a long way to go. The only thing, Nelson Mandela once has said that technology is a strong tool that can transform the billions of the lives, that can transform the countries. And yes, technology, when we talk about the technology, we have to think about the technical education system of this country. A time has come to redefine the education system itself. The objective of the education is missed somewhere. Our students, our faculties, our even the parents are mistaking or misrepresenting the education. A survey was conducted by MIT in India, and that was on the students studying in IITs and NITs. 6,500 students were interviewed, and only one question was asked. And the question was, why you are studying into the institutions, premier institutions like IIT and NIT, and that too engineering. 87% students gave a similar answer, and answer was very shocking. And the answer was to get a good job, to secure a future. So when the cream of a nation thinks of the security, when the cream of a nation thinks of a job, then where is appetite left for research? Where is appetite left for the innovation? Honorable APJ Abdul Kalam once said that without innovation, there cannot be a nation. And Swami Vivekananda once said that when the objective of in the country, when the objective of the education is to get a job, such country will never produce an engineer. Such country will never produce an entrepreneur. Such country will produce only slaves. And my dear friends, the time has come now. We all talk about the innovation. We all talk about the research. We talk about the industry institute collaboration. Yeah, Maharajan sir was talking about the need of the industry and the expectation of the industry and what we are delivering to the industry. So that we are together but still not together. Industry and institution relation is just like a sea and seashore. They're together, but they're still not together. So that's the issue. I think the attitude, research attitude, and the innovative approach is to be inculcated into the students. Students must be made aware that they're not going to learn, they're not going to get educated for themselves. The time has come to learn for the nation, to learn to build a nation. And to build a nation, each one of us has to contribute in the national development. And to make everyone capable of contributing into the national development is the responsibility of the education system. And I think making our faculty aware of what exactly is happening around them, what are the new technologies, what exactly is happening across the globe. Unless our faculty knows it, it cannot be percolated to the students. And this is a little attempt with the help of the BNY to bring the such opportunities, such platforms for the teachers to learn new things, to come across the latest happenings in the world, and ultimately think about how the student fraternity will be get benefited out of this. I think yes, you all will have some nice takeaways from this one-day workshop, and definitely it will benefit the students. IST will always be with you all in all such endeavors. Jai Hind.
Thank you, sir. Thank you for inaugurating the program and sharing your thoughts with us. Thank you for your inspiring words too. As we come to the close of this inaugural function, I invite Dr. K. Saravanan, Professor, Department of Information Technology, RMK Engineering College, to deliver the vote of thanks.
Respected chief guest of honor, distinguished speakers, esteemed dignitaries, respected principal, HOD of IT, faculty members, and dear participants. It is my proud privilege to propose the vote of thanks for this inaugural session of the ISTE-BNY Knowledge Enhancement Program, 6-day faculty development program on quantum-assisted federated learning for secure distributed intelligence. First and foremost, I extend our heartfelt gratitude to our respected chief guest, Dr. Pratap Singh Desai, President, Indian Society for Technical Education, IST, New Delhi, for gracing this occasion and delivering an inspiring inaugural address. Your valuable insights have truly set a strong foundation for the sessions ahead. I express my sincere thanks to our distinguished guest of honor, Mr. Maharajan Muthuswamy, Director BNY, for gracing this event with his valuable presence and felicitating the audience. Sir, your insightful words and inspiring thoughts have truly enriched us and provided a new perspective. Your contribution has made this session both meaningful and impactful. I would like to place and record our deep sense of gratitude to our respected principal, management, and HOD of Information Technology for their continuous encouragement, support, and guidance in organizing this program successfully. My special thanks to the ISTE-BNY Knowledge Enhancement Program for providing us with the wonderful opportunity for organizing such a relevant and impactful FDP. We express our sincere gratitude to the respected resource person for graciously accepting our invitation to serve as the resource person for this 6-day FD faculty development program. I extend my appreciation to all the organization committee members and faculty colleagues whose dedicated efforts, planning, and coordination made this inaugural session a grand success. I also thank all the participants for your enthusiastic registration and active presence. Your involvement makes this program meaningful and effective. Finally, I express my sincere thanks to everyone who has directly or indirectly contributed to the successful inauguration of this FDP. With this, I conclude my vote of thanks. Thank you all.
Thank you, sir. With this, we conclude the inaugural session of this faculty development program. We thank all the dignitaries, speakers, and participants for making this session a meaningful and successful. Wishing all the participants a highly productive and enriching learning experience over the next 6 days. Thank you once again. Have a wonderful day. Let's have a break, participants, and we'll start the next session at 11 a.m. today morning. Thank you all. Thank you so
Thank
much.
you, sir. Thank you,
sir.
sir.
Thank you. Thank
Thank
you.
you.
Thanks,
Thank you.
everyone. Good day.
Thank you, Desai, sir. Thank you. Thank you,
Thank you.
Maharajan, sir. Thank you, sir.
Thank you, sir. Thank you.
Thank you, madam.
Thank you, sir. Thank you.
ஆயிஷா லீவ் ஆகலையே ஒன்லி திஸ் டைம் கொடுத்தாலும் லீவ் ஆகலையே
வருதா மேம் இன்னும்
வேளாண் நல்லாச்சு. Ma'am, very good morning, ma'am.
Good morning, sir.
Yes, ma'am. Yes, ma'am.
Shall we start, sir?
We'll start, ma'am.
Welcome back, participants. A good morning to all the respected dignitaries, faculty members, and participants. Our next session is Introduction to Quantum Computing Principles. It's my great honor and privilege to introduce our esteemed resource person for today's session, Dr. P. Mallika. She is currently serving as a professor and head of the Department of Computer Science and Engineering at the National Institute of Technical Teachers Training and Research, Chennai, under the Ministry of Education, Government of India. She is also an adjunct professor at NIT Meghalaya. With an illustrious career spanning 33 years, she has made remarkable contributions to teaching, training, and research, driving innovation and excellence in technical education. Dr. Mallika holds a BE in Computer Science and Engineering from the University of Madras, as MS in Software Systems from MITS Bilani, and MS from Anna University, and PhD from the University of Madras. Over the years, Professor Mallika has played a significant role in capacity building by coordinating more than 350 faculty development programs and serving as a resource person in over 475 training programs. She has also contributed to international initiatives, training educators from countries like Bangladesh and Tanzania, and coordinating several prestigious ITC sponsored programs focusing on educational media production for e learning, advanced pedagogy and IT skills, blended learning and innovative pedagogy in the era of AI, and instructional design for e learning. She has also contributed significantly to digital education through Swayam Moose courses and e-content development. We truly privileged to have such a distinguished academician and inspiring personality with us today. Now, I request Dr. P. Mallika to take over the session and share her valuable insights. Over to you, ma'am. Please, ma'am.
Thank you. Thank you very much for your kind words. I will also share my PPT. Just give me a minute.
1 second.
So for me, the sharing is not turned on.
1 second, ma'am. 1 second. Yes, ma'am, proceed, ma'am.
Okay, right. You're able to see my screen, isn't it?
Yes, ma'am.
Okay. One second. Very good morning to all present here. It is a nice opportunity for me to share my learnings with you, because this is a very new area and most of you and most of our computer science people will be working on it. And it is totally going to be a different scenario, which will be very different from our classical computing. Okay, so in this session, I will be Here, yes, are you able to hear my voice?
Yes, ma'am. Yes, ma'am.
Okay. No, there was some
Yeah.
Okay. So this is going to be totally different from what we are working now, right? Whatever we are working, maybe let us say your mobile phones or laptops or any computer systems, these are all coming under the classical computing, right? But now people are started working on quantum computing. So, what is it? And we will understand what it is because in India, so far, now only people have started, but the big giants like IBM and Google, they have established a quantum computer and which has been dedicated to healthcare sector and other things. In India, we have to start it, and lot of entrepreneurs and startups are working on it, pooling lot of money and other things, right? So with this introduction, let me go to the next slide. See, this quantum computer is a machine that performs calculation based upon the laws of quantum mechanics. Okay, it is based upon the quantum mechanics and quantum physics, which which is the part which is a behavior of particles at subatomic levels. Okay, so then if you look at the quantum, you can see that they envisage that there are many possibilities and applications starting from telecommunication, life science, transportation, finance, healthcare, petroleum, manufacturing, and logistics. So, whichever has not been or very difficult for us to solve using the classical computing, they are trying to solve through quantum computers. Okay, quantum computing. So, here it is based upon the laws of quantum mechanics and which is the behavior of the particles at subatomic level. When I say subatomic levels means you have to imagine electrons, photons and all those things, right? So here quantum mechanics is a theory that describes the behavior of the, once again, this must be hiding for you. Is it visible?
Yes, ma'am, it's clear only.
Okay. Why it is? For me, it is not visible. My screen is visible to you?
Yes, ma'am, it's visible. Quantum mechanics.
But for me, it has gone.
Ma'am, now stop sharing and again share, ma'am. Then.
Okay. Sure. Hope you are able to see my quantum mechanics. Huh?
Yes, ma'am. Yes.
See, this, yeah, I was trying to do this. The quantum mechanics is a theory that describes the behavior of microscopic systems such as photons, electrons, atoms, molecules, etc. So when we always talk about photons, electrons, atoms, you must be knowing it is it is very difficult for us to understand because we are not able to see it in our naked eye, right? So this is where the complexity or understanding the quantum mechanics becomes a bigger issue for each and every one of us. but the scientists are working on it, and they are describing the behavior of these microscopic systems such as photon, electrons, and other things. So Richard Feynman, like he's a very big scientist who is a great scientist in quantum mechanics. He says, "No, you're not going to able to understand it. You see, my physics students do not understand it either. That is because I don't understand it. Nobody does it." The theory of quantum electrodynamics describes the nature as an observed from the point of view of common sense. So, and it agrees fully with an experiment. So I hope that you can accept nature as she is absurd. Okay, this is what he has quoted, because we are trying to understand the nature, how it behaves, how the universe are there, how it is all moving in one particular direction, who is controlling it, and how it has been controlled. So many things. No, if you go take about the universe and other things, there are a lot of things which the science has to discover it. Fine. So coming to this quantum mechanics and classical mechanics, what is it? See, classical mechanics deals with the macroscopic particles, okay? Whereas the quantum mechanics deals with the microscopic particles. And our classical mechanics is law of motion and Maxwell's electromagnetic wave theory. But here it is based upon the Schrödinger equation and the Planck's postulations. That is, here it is not continuous, it is a discrete value of energy that is admitted or observed. Okay, that is the origin, or that I can say that is a principle of quantum computing. Okay, they are discrete. The energy is discrete. Whether it is emitted or observed, they are only discrete. That is the first principle which we have to remember. And any amount of energy may be continuous or observed continuously in classical. Here it is discrete. Then the state of the system is defined exactly by specifying their positions and velocities. Because of the Heisenberg's uncertainty principle and de Broglie's hypothesis, the dual nature of matter, that is, it can be both as a particle and also a wave. At one state, you can consider that it's a particle. In another state, it is a, or it can be the same thing can be as a wave. So that we have to understand. It is both a particle and a wave, and the state of the systems cannot be specified exactly. Okay, so that is where another thing we have to remember. So here the state is defined by their position and their velocity. Here the state is defined as a particle or as a wave. Okay, the state of system cannot be specified exactly. In classical mechanics, the future state can be predicted with certainty. Here, in quantum mechanics, it gives probability of finding the particles at various locations in space. So if you see how it is different from the classical mechanics and quantum mechanics, it is macroscopic. Here it is microscopic, because everything is based upon the photons, electrons, and atoms and molecules. So microscopic element. Here the equation, that is the Schrödinger equation, is the base of it. Then here it is, we all operate in the classical thing, it's all Newton's law of motion and Maxwell electromagnetic wave theory. In classical mechanics, any amount of energy emitted or observed is continuous, whereas in quantum mechanics, they are discrete. That is the first principle we have to understand. So the value of the energy or emitted or observed, that is called the quanta or quantum. That is the origin of that. Okay. then the state of the system is definitely, or you can say it is defined exactly by specifying their positions and velocities. Whereas here, the state, it can be a particle or it can be a wave. Okay, so from this, what you can understand is it is microscopic, it is discrete, that is the origin of quantum or quanta, and then the particle, it can be both a particle and a wave. Okay, and it cannot be specified, okay, at exactly what it is at one state. And here the future state, that is in classical mechanics, the future states can be predicted with certainty. Here the probability of finding particles at various locations in the space. So usually we explain these things with the, let us say, a coin. Okay, you take a coin, you have two things, that is head or tail. Okay, so, or if you take a switch, you can switch it on or switch it off. So better you take that first example, the coin example. It is 0 or 1, head or tail. In quantum mechanics, when you spin the coin, okay, so when you toss, no, when you toss the coin, it just flips, no, like in the air it flips. And then it may be 0 or 1, 0 or 1, 0 or 1, 0 or 1, and then finally it will be some, when it falls down, it is there. So this in between, no, you cannot predict whether it is 0 or this is 1. That is called superposition, or that is the state, right? So we will be understanding more about it. Then comes the, like let us say, if you take a classical computer, our what we are using, our laptop, desktop, mobile, and all these things, you know what are the components of the laptop or desktop. Okay, keyboard, mouse, LCD, display, CPU, processor, and all those things. Okay, this you will be aware of it, right? Like let us say, if you're taking a quantum computer, how it looks, it is totally different. Okay, the people say, yeah, to come into the market and other things, now it is in research labs only. Okay, so it will take more than 10 years, right? So that is what they predict. So here this Cleveland Clinic and they unveiled the first quantum computer dedicated to the healthcare research. Okay, in 2023, it was done. Okay, that is the IBM Quantum System 1. This is called, whatever the picture you're seeing, it is an IBM Quantum System 1 at Cleveland Clinic, which their team of world-class researchers are now exploring it and uncovering the new scientific advancement in biomedical research. Okay, so this was said by the Arvind Krishna, who is IBM chairman and CEO. Okay, so a lot of things. See, why they have to go for all these things? I will also answer that question. And this is a picture which I took it from Google's quantum computer. That is, you can see Sundar Pichai is standing beside his Google's quantum computer, right? So this is what. So actually, if you look at these things, no, you can see so much of copper and other things, so many wires, and where is the chip, all those things, right? The hardware, if you look at it, yes, there are several competing modalities. Like they use different things. Every lab, IBM uses in a different way, then Google and many other things, right? So they used the chilled circuits, trapped ions, that is ion Q, using individual atoms led by lasers, and photonics using particles of light. Okay, using particles of light. So the challenge here is, see, the maybe I this will I can discuss later also. decoherence qubits are incredibly fragile. That is, see, I'll show this figure first. If you look at this is the architecture of this quantum computer, and see that this is a chip. You're able to see? So this is the chip. Okay, this chip is kept at what temperature? Minus 273 Celsius. Okay, minus 273 Celsius or 0.01 Kelvin. Okay, so that is the temperature it requires to be kept. Imagine so much of coolant is required. So a refrigeration unit, coolant is coming here, and this chip, the quantum chip, is kept in that temperature. And these wires, so it will be in the beneath of that thing, which will be later for all these things 3K. Then this can be kept in 50K. Then this is 27 Celsius. 27 degrees Celsius, like that it is there. So max from minus to 27 Celsius, minus 273 Celsius to 27 Celsius, this has to be maintained, right? And just imagine it is all photonic particles, and there are possibilities. Where is it? Can I move to the one sec. This I can grab it up. So the challenge here is that decoherence qubit are incredibly fragile. So any heat, vibration, or even a stray, that is cosmic ray, can cause decoherence. What is it? It can have the quantum state can collapses into noise. Something will happen. So that is why we need quantum error correction. That is the biggest challenge. Okay. So because of this, it has to be kept in such a cool place. Any heat or vibration or any ray can cause decoherence, right? Right. Oh. Yes. So if you look at the classical and quantum computer, the classical computers will be operating on bits, zeros or ones. Here, quantum computing will be operating 0 or 1 or psi. Psi is, it can be 0 or it can be 1. Just imagine flipping the coin. So head or tail. In between, when you toss it, there are many what do you call states, no? It can be 0 or it can be 1. So that is the other one. So it is called qubit. Okay, 0, 1, or it can be 0 or 1. Okay, so that is there. So the operations, since it is 0 or 1, very definite, the operations what we do is deterministic and sequential. Whereas in quantum computing, it is all probabilistic. It can be 0 or it can be 1. Probabilistic and parallel. Parallel is, how can I explain this? Yeah. See, let us say you're going to a library and you wanted to find some term. Don't imagine about Google search or AI and other things. Physically, we are going to a library. You are going to search maybe some keyword which you want to learn, or some topic which you want to learn. So you're scanning through a book. No, you're not able to find out. Then you're going to the next like that. So how much time it will take? Let us say, for example, like you simultaneously, you're reading all the books, okay, system. Now, how the system is reading all the things, like that simultaneously, you're going to do that operation. In that case, that is called parallel, okay, that is called parallel. So it is probabilistic and parallel, right? And then mathematical model is, it is here Boolean algebra on binary numbers. Here it is linear algebra on complex numbers. Okay. And then if you look at the parallelism, here limited classical parallelism, like you have multi-threading and other things, that is limited. Here quantum parallelism via superposition and entanglement. We will learn what these principles of quantum mechanics, what is superposition and what is entanglement, right? And then you have this energy options also, that is energy consumption, sorry. Relatively high energy consumption due to heat dissipation. Here potentially low energy consumption, still it is experimental, okay? And then scalability, highly scalable with advancement in classical hardware. Here it is limited scalability due to the current quantum hardware challenges. So this is the basic differences. Here bits, zeros or 1, here it is qubits, 0, or we can say ket 0 or ket 1, or it is ket psi, which is either can be 0 or 1. So here it works on probabilistic and it is parallel, okay? And everything is represented as a matrix, okay? And then linear algebra on complex number. So if you want to work or if you want to understand quantum mechanics or quantum algorithms, then you should be having the mathematical foundations on linear algebra, on complex numbers, okay? So that is very much required to understand and to go forward about it, right? Now, so yes, it is saying multiple state quantum mechanics. Here the physics is classical, here it is quantum mechanics, this, right? What is a qubit? What is a qubit? So here, qubit or quantum bit is built using the subatomic scale particles like electrons or photons, using the particles properties like spin, polarity, intrinsic angular momentum. Okay. See, if you look at this, this is called the Bosch sphere. Okay. This is called the Bosch sphere. So when it is that Z, that is that blue color, no? So it is up or down. Okay. So that is up, let us say it is 0 or this is 1. Okay. So 0 or 1. In between, see, when it moves, so moves an angle. So if it is 0 angle top means it is 0, 180 it is 1. And then if let us say the coin is spinning or if the particle is moving, right? So it moves with an angle theta. Okay, you take the radius like theta. So if you can move on this, on the outer, what is it, circle or hemisphere of it, the outer part of it. So you can see different, you can have so many points, isn't it? With this different angles, with measured with an angle, what is it? Theta. Then there can be another angle also when it spins this way. So that we call it as a psi, and when this we'll call it as a theta. So here it can be the spin of an electron, which can be in any one of these three states. It can be up or down or superposition. Okay. The polarity of the photon, which can be in any one of these three states, that is horizontal, vertical, or superposition. So when it spin up 0, then a down 1, in between it can have the superposition state. Okay. So the representation of data, it is by qubit. There in classical computers, we have bit. Here it is qubit. So a bit of data is represented by a single atom, that is, it is in one of the two states denoted by 0 or 1. Okay. So a single bit of this form is also known as the qubit. A physical implementation of qubit could use the two energy levels of the atom, an excited state representing 1 and the ground state representing 0. So you can also see that it is a light pulse of frequency gamma at an interval of time, interval of t. Okay, so this is doing it, right? So when it is in ground state, we call it as 0. When it is excited, we call it as 1. In between, there can be many states also. So the key properties of qubits, that is the core idea, is superposition. So that is the first principle is it is discrete, and then it can be a particle or a wave. And the next one, we are going to talk about the superposition. A qubit can exist in a combination of zeros and one at the same time. This we have seen. So I think you can understood. Only when you measure the qubit. So at any state, see, let us say, even you can see that birds flying, no? Let us imagine a hummingbird flying. So when it's flapping its wing, whether it is down or up, we do not know. When it stops, only we can say, or when it just once, like when it got trying to end it, no, so it flaps. 0 or 1, 0 or 1. At one particular state, okay, you measure it either to be 0 or either to be 1. So the probability, if you take, it is 50. It can be 50% 0 or 50% 1. This or that. But okay, it can be anything, right? So the representation, a single qubit can be forced into a superposition of two states denoted by addition of state vectors. So 50% it can be in zero state, 50% it can be in 50-50. Okay, 0 or it can be 1, right? So you can write it with this notation. Okay, the psi is the superposition where you can say alpha or you can say beta. Here I have said alpha 1 and alpha 2. In some of your articles or books, they will represent it as alpha get 0 plus beta get 1. Okay, so that is how it is represented, where alpha and beta, or you can say because this is on the top, so better we can use alpha and beta, where alpha and beta are complex number, where alpha square plus beta square is equal to 1, because complex numbers, no, that has been represented like that. Okay, which you cannot solve. Minus of what is complex number, you must be knowing, right? The, like, let us say if you want to solve square root of minus, then we need complex numbers to represent it. So the qubit is in superposition and it is in both of the states, either 1 or 0 at the same time. Okay, so representation of data. Hope you are able to understand. If you are, I am just starting in the basic level only. If there is any questions, you can put it in the chat, or at the end of the thing also you can do it, or you can unmute yourself and then ask me some questions if you have, right? So we are just talking about one bit. Say, consider that, let us say there are 3 bits, qubits. So how will you write it? An equally weighted superposition if all possible states would be denoted as, say, 3 bits means 0, 0, 0, 0, 0, 1, 0, like that. You will have all combination. It will have 1, 1, 1. Not so many things. So it will be 2 to the power of 3. So 1 by 2 to the square root of 2 to the power of 3 plus, like that you will have it. So this is the representation of 3-bit qubit register. Okay. So in general, n qubit register can represent numbers from 0 to 2 to the power of what is it? 2 to the power of n minus 1 simultaneously. It sounds good, isn't it? When we attempt to retrieve the values represented within a superposition, the superposition randomly collapses to represent just one of the original values. Okay. So in our equation, if you see this, in our equation, if you see that psi, that is, this is alpha 1, or you can say alpha and beta, right? Alpha get 1, get 0 plus beta get 1. Alpha and beta are the probability of superposition collapsing to 0. So this in a balanced superposition, alpha is equal to 1 by square root of 2, where n is the number of superposition. So then what is entanglement, right? What is entanglement? Superposition, now you understand there is a third thing, either 0 or 1. So what is entanglement? One second. Okay. So first we have seen the superposition. So that is an ability for a quantum system to be in a multiple stage, okay, at once. So mathematically we represented what psi is equal to alpha 0 plus alpha get 0 plus alpha get 1. Okay, so where alpha and beta are the complex probability amplitudes. See, they are measured as amplitudes. So because it is like a wave, no? So the rule is that the total probability must be equal to 1. So anyhow, it has to end up with 1. So alpha square plus beta square is equal to 1. Now we will see the entanglement. What is it? Okay. So see, I can also refer to this Einstein, right? So Einstein called it as a spooky action at a distance. When two qubits become entangled, their states are linked. For example, I can say, yeah, you are sending up, or let us say you have a set of balls. Here I have red balls, and you are sending it to US. If you know what is the color of the ball here, and if you are able to predict the other color, what is in the US, you cannot go and see. That one is, if you want to know the color, you have to travel to US and then find it. That will cost you, like you have the travel time and other things. Imagine that by knowing the color what I have it here, I can also know what will be the color in US, for example. This is a very trivial example. Okay, so in that case, if I know and if it is predicting correctly, then these two things are entangled. They say they are linked. So measuring one instantly determines the state of the other, regardless of the distance between them. So when you measure instantly one thing, and if you are able to measure or determine, if you are able to determine the state of the other regardless of the distance, then then it is called they are entangled. So what you can understand from this, two or more qubits become entangled. The state of one qubit is linked to another. So because of this only, it allows massive parallelism and coordination that classical computers cannot replicate, right? So for example, even a simple example I can say, so when we want to multiply two numbers, right? When you want to multiply two numbers, we use first we can, if it is very small, we can do it by our manually. If it is a little bigger number, then we use a calculator. And if it is still bigger, then we go for what is called the computer to calculate. But anyhow, we can use these devices to calculate a bigger number. But if you put it as a ulta, like let us say, for a given number, what are the possible things? What are the two numbers? If you multiply, what the number you get it? Okay, so this is multiplication. This is finding the factors. If you give a bigger number, even for our classical computers, it will take lot of time to calculate it. So it will take lot of time to calculate it. Right? So it will take lot of time to calculate it, even days like that, if it is a very big number. So which cannot be which cannot be handled by the classical computers, right? So in that case, what you this parallel here, it can do parallelly. Okay, one second. Yes. Able to see this? Yeah. So measuring one instantly affects the other, even if it is far. So this enables extreme fast correlation and powerful computer, that is parallel computation. Then the third one is called, even you can say that interference. So we have seen it is a discrete, it is a particle or a wave, and then superposition, and then entanglement. Entanglement means what? If one, when you are able to determine what is the other one, even if it has been separated by the distance, okay, then you say that these two things or these two states are entangled. So that principle is being used in parallelism. The next comes the interference. What is it? So here the quantum states can reinforce correct answers and cancel incorrect answers. That this is how quantum algorithms amplify the right solution. What do you mean by that? See here, this is the secret sauce. Okay. So just like noise cancelling headphones, okay, which you use out of space, that is the sound waves to cancel the noise, or quantum. Here the quantum algorithms use interfaces. Okay, so what it does, it amplifies the probability of the correct answers. That we call it as a constructive interference, and it will cancel out the probability of wrong answers. That is called the destructive interference. Okay, if you look at this diagram, see, if you see the crust, the crust and crust, if you add it, then it will amplify, right? If you see that dip, then if you add it, it becomes minus, that is 0. So here how it works, see, it all works like this: quantum logic gates. See, unlike classical gates like AND, or NOT, quantum gates must be reversible. Another one you have to find, note it down. The quantum gates must be reversible. So we can represent them as a matrix that rotates the qubit states around the Bosch sphere. Remember, I showed it in the previous thing. Okay, so here what we call this operation, due to the nature of quantum physics, the destruction of information in a gate will cause heat to be evolved, which can destroy the superposition of the qubits. Okay, so if you see that quantum gates are similar to the classical gate, but do not have to regenerate output. Their original input can be derived from their output state uniquely, and they must be reversible. This means that a deterministic computation can be performed on a quantum computer only if it is reversible. Okay, so luckily it has been shown that any deterministic computation can be made reversible, right? So yes, so what is it, how it can be implemented? So we call this Hadamard gate. Okay, the simplest gate involves 1 qubit is called the Hadamard gate. It is also known as the square root of NOT gate. It is also known as the square root of NOT gate. It is used to put qubits into superposition. See, you can just note it down, right? Yeah, see here, it is state 0, and then it goes to another one, and that is it can be state 0 plus 1, and then it reverses it. Okay, it is state 1. So two Hadamard gate used in succession can be used as a NOT gate. Okay, so when you have two gates, okay, so what it is having capacitors and okay, whether I have the diagram, yeah. A gate which operates on 2 qubits is called the controlled NOT, CN gates. If the bit is on control line is 1, they invert the bit on the target line. Okay, so this is what, so it is 0 and this is 1. Okay, so let us say 0 0, the output will be 0 0, 0 1, it will be 1 1, and 1 0, it will be 1 0, and if it is 1 1, it will be 0 1. So the CN gate has similar behavior. If you look at the output, if you see the output, it is what? When both are, what is it? Yeah, it is XOR, no? It is XOR with some extra information to make it as irreversible. So if it is both 0 0, you are getting it 0. If it is both 1 1, you are getting it what? 0, right? So if you see this Hadamard gate, it has been represented by a vector matrix, okay, matrix, and then it is if you look at it, it is see 1 by square root of 2, and it is represented as 1 1 1 minus 1. This is what the interference. See, this is 1 and this is minus 1, negation of it. Okay, so interference property is being applied here. Okay, so this is called one gate. So if you have two gates in sequence, then it becomes a NOT gate, right? So the smallest unit of information in the quantum computer, it also represents the states of the wave function psi in Schrödinger equation. A qubit may be in on state or off state. There are many ways to implement a qubit. For let us say a nuclear spin, up means 0, down means 1, or photon in a cavity, 0 photon or 1 photon, or energy state of the atom. Okay, if it is normal or stable, 0. If it is excited, it is 1. Polarization of the photons, many other things. See, each and every people, they do it in a different way. So here the computing loop, if you see, it is a microwave loop which is being used by Google, IBM, D-Wave, and other things, right? Whereas the trapped ion, the Honeywell and ion Q, they uses this way, and silicon quantum dots, Intel has a different way of producing this qubit, right? So what we have to understand is the hardware component may be different, but the properties, what we are learning and what we have to implement in the algorithm is different, right? The different means it can be based, the functions are same, the implementation of that in the hardware part may be unique for different one. They are trying to see whatever how they are studying this, and they want to the mathematical models has to be proven, no? So that is why they are constructing these things to prove that the mathematical representation of this one. Okay, the Hadamard gate is widely used to initialize the qubit into superposition at the start of the algorithm, enabling quantum parallelism where many computational paths are explored at once. Okay, it appears in a key protocols and algorithms such as Dusach-Joshua algorithm. Then you can say in quantum teleportation algorithm, quantum key distribution, and many error correction schemes, making it as a central building block of quantum circuits. See, it is also used in networks, particularly in security and other things. So if you want to find, let us say, for example, like this, you have a number lock. Okay, so number lock. So the key, you have two things only. Just for simplicity, we are saying. Okay, usually you will have 3 or 4, no? So depending upon the number locks. So I'm just taking an example of 2. So the key is, let us say, for example, we'll take it as 1 and 0. Okay, so you do not know, the other person wants to open it, they do not know, so they'll be trying 0 0, no, it didn't work, then 1 1, it didn't work, then 0 1, it didn't work, so then 1 0, it worked. So the key is 1 0. So at the fourth time only it has been done. Imagine in quantum computing, or at the simultaneously there will be four things they'll be trying at the same time. One will be trying 0 0, one will be trying 1 1, and another one 1 0. So the time taken to decipher or to find out or to solve, it will be less. That is what, just imagine, for 2 we are saying 4 thing. Imagine it's a very big 64-bit or 32-bit. Imagine how fast it can do. So that is where, which we cannot solve through classical computers, which will take long time for us to know about it. We are trying to, the scientists and researchers are trying to solve through quantum computing. So you are able to find the solutions very fast. Okay, how it can be done in a classical computer? It is very slow because it is a limited parallelism only we can have. Here it operates like that, and because of the superposition, entanglement, and interference, the properties, the principles of quantum mechanics helps us. So it is mainly useful in many, what do you say, healthcare, drug discovery, then in networks, that is security purpose, where we have so much of issues which cannot be solved. It has been solved using this quantum algorithms, right? Quantum mechanics and all this. So the logical gates, the quantum logical gates, unlike the classical gates like AND, NOR, quantum gates must be reversible. See, there it is not reversible. Here in quantum circuit should be reversible. We must represent them as a matrix that rotate the qubit state around the Bosch sphere. Hadamard gate puts a qubit into a superposition. C0 gate, that is, it is like an if-then of the quantum world, essential for entanglement, If I know this, I can predict that. So one state, if I am able to measure, I can determine what is the other state. That is called the entanglement. So C gate operates like if-then. If this is red, then that should be also red. Or if this is whatever it may be, right? Okay. If it is 1, then that should be 1, like that, or otherwise. So the heavy hitters, like when you are working on this quantum computing, the first two algorithms everybody should know or we try to understand and implement is the SHOR algorithm. Okay, Schrödinger algorithm, where factor large integers exponentially faster than the classical computers. So it is the end of encryption talks. Okay, so it can factors large integers exponentially faster than, it is not like linear, it is exponentially faster. If the more the qubits, the more the faster it is there. Okay, exponentially faster than the classical computers. Then the Grover's algorithms, it searches unsorted databases in time. See, when you want to sort anything, first when you want to search anything, it has to be sorted, right? So mostly it has been done like that. So here it can search unsorted databases in time. Fine. So if you look at, well, if you just summarize what we have learned, so you can see that the quantum computing calculates with qubits, which can represent 0 or 1 at the same time, which is called as a superposition. Then, of course, classical computers, it calculates with the transistors. It can be either off or on, or switch on or off. It can be zeros or one. Okay. Whereas the power increases exponentially in proportion to the number of qubits. If you see what is how many, the biggest computer, how many qubits, like IBM in 2023 or 4, it has done 127 qubits quantum computer. Okay, 127 qubits quantum computer, it is that. If you want to work on it, IBM, you can also, they give us the platform to work, but they don't give you 127 qubits. So they give you like 4 or 8, depending upon, because we have to pay for that, right? So then it is possible. And then the power increases exponentially in proportion to the number of qubits. So it will be much, much faster. So exponentially, it is much, the power increase. Here, it is linear relationship. So it is number of transistors and other things. The quantum computers have high error rates. I said, no, it should be maintained in a very cool place, heat, vibration, and so decoherence will happen. So we should have quantum error correction. That is the biggest challenge in quantum. We do not know, like if any small disturbance or noise, it may end up with some errors. So it is high error rates and need to be kept ultra cold. Then classical computers have low error rates and can operate at room temperature. And then it is, well, see, where do you see you to quantum computers will not come into practice at the or to our tables in the maybe it will take 10 years to have that like that. And it is not, see, for our daily data processing task and other things, we have very good computers. If you want to work with AI and ML and other things, where you have to process this large data images, you need GPUs. Okay, but whereas if you want to solve the real world problems like optimization problems, then data analysis of a large way, and simulations, so where you want to do it very fast, then the well suited thing is quantum computing. Okay, so it will take time. The people will, material science people, all those people will be working with physics, quantum physics, material science, computers, computer people will be working on the algorithms, but how to make the hardware part, the electronics and other people, mostly who has the interest on that, and researchers will be working to make it possible, all those things, right? So the most everyday processing is best handled by our classical computers. So here you have zeros and ones. Here it has this Bosch sphere. You have to understand. Okay, it is 0 or 1, or it can be both. Okay, in different angles, or all those things. Okay, 0 or 1 exists at a time. Okay, when you determine or when you measure, then it is 0 or 1 only. It can be 0 or 1. Then it concludes to be 0 or 1 when you measure it or when you determine it. Okay. Why qubit matters in life science? So we will see some of the applications where this qubits matter. Okay. That is particularly when you take the life science and healthcare. Right? The biological systems operate at the molecular and atomic levels, which are quantum in nature. Okay, so the drug discovery, which simulates molecular interaction, protein folding, explore complex energy landscape, then genomic what is it, optimization, faster pattern searches, and then quantum machine learning. Now people are working on it, no? Like one of my scholar is also working on it, on how to use quantum machine learning to find Alzheimer in the early stage itself. See, one is to identify any disease, and then see how whether it is at stage 1 or like that, and then you detect. So with your many what is it, all the inputs, how we can give, okay, this person will end up in Alzheimer or will end up in some disease. So that is with a lot of permutation combinations, or with lot of data analysis. They are trying to do it. Okay, so that is quantum machine learning, which improves us the diagnosis, even not only diagnosis, predictions, and other things. So biological systems operate, and even for with the IE and all, there are many people are working with quantum machine learning, study of IE, like Shankara Nethralaya, and then one institute at in Delhi. They are all working on quantum things, okay, which has been sponsored by other country collaboration. They are working on it. So biological system. So it is essential. Not the computer people should also work in a multidisciplinary. Okay, how you have to improve the algorithms to, because then only we can solve the problem. So there are so many things in nature to understand or to decipher what it is. Okay, so it is very much essential. And then quantum computers exploit superposition and entanglement to process many possible states in parallel, which can give exponential or polynomial speeds up over the classical computers for certain tasks like um, molecular simulation, optimization, and some type of machine learning. So in life sciences and healthcare, these tasks map naturally to the problems such as simulating proteins, optimizing treatment plans, or classifying complex images. Okay, so let us say, for example, I'll give you one thing which I had a discussion with a medical expert. So he says, okay, when a patient comes, then we take all the details, and then we will try to okay, it is not this. They will just neglect, or they will say, okay, every test, no, whatever test they do it, they'll say, okay, this is not this, this is not like that. They try to do it, decipher it, and then finally say, okay, what would be the issue, or what will be the problem of it. So they do, how do they find out is by taking different tests. See, even if we break our legs and other things, no bone, immediately you first thing, okay, you go and then say the doctor, if it's an expert, he will touch and say, okay, this may be a very minor thing. You can put some band-aid and then you can go. Or if there is some swelling or any other thing, then we'll say, okay, you let us take an x-ray. Okay, in x-ray also it happens to be fine, but still there is swelling and other things. Then he'll say, okay, go and take an MRI scan and come, right? So in that, any ligament tear is there, or any like ligament tear is there, they'll able to find out. So one by one only they are able to do it. I'm just telling an example. So like that, if a person comes, if you want, okay, he is very tired or sick or something like that. So if you are using this, his all his data, right? Then so at one instant or at one time, you can find out what will be the disease diagnosis. So it is not stage by stage. It is not linear. It is not linear. Okay, one, okay, not this, not that. It will take some time, no? So immediately, if a patient comes, okay, this is an issue the doctor says, or it help by looking all using the computers, it gives you all the combinations and taking his DNA and other things, processing it. So DNA processing and all, it takes a lot of time. So if it has been done very easy, fast, then the diagnosis will be improved. That is where this quantum computing will be very helpful, and that is where people are working. IBM has donated this, not donated, they have installed this IBM One, Quantum One computer for just only for the healthcare. Okay. So in life science and healthcare, these tasks map naturally to the problems such as simulating proteins, optimizing treatment plans, or classifying the complex medical images. Okay. So drug discovery and design. Again, this is another one which has been used. Quantum simulation of computer systems can in principle model electronic structures and protein ligand interactions with higher fidelity than the classical and which may shrink search phase and reduce wet lab iterations. So that is what. So early study shows quantum enhanced or hybrid workflows can help screen ligands for difficult tasks such as CARAS and other undruggable proteins, mainly as a proof of principle demonstrations. Okay. And then in biomolecular and system biology simulation, here quantum algorithms are being explored for protein folding, reaction pathway, and other complex biochemical dynamics that are computationally irretraceable at high accuracy on classical hardware. Okay, see, even we just take our brain. Our brain has 86 billion neurons. Our brain has 86 billion neurons. So we are using this neural network for deep learning algorithms, no, mimic, right? So the instead of machine learning, this deep learning gives you a better result because it is working like based upon the neural network RNN, CNN, LSTM. You are able to predict it almost near 99%, 99 or something even. You are able to achieve it. But what happens here? The delay, right? Particularly in um, uh, biology or in cryptography, there are some issues. So this classical computers, which will take more time, now they are trying to solve those issues with quantum computing because of the it is all, see, it is all it is wave, amplitude, and then you have the superposition, entanglement, and interference. These properties help them to do it in parallel. Okay, so that is what. So better quantum scale models, misfolding and binding would eventually inform integrated therapies for disease like Alzheimer, Parkinson, and some cancers also. So this is what one of our person is working on Alzheimer. So then medical imaging and diagnosis. Quantum machine learning methods such as quantum support vector machines, quantum convolution neural networks, and hybrid quantum classical models, hybrid. So we can try with that, or being tested for tasks like brain tumor detection, skin lesion classification, and COVID-19 imaging. A recent hybrid QML, that is the quantum machine learning model, improved blood flow imaging in laser spec contracts imaging up to nearly 26% in prediction accuracy over the classical baseline in synthetic data, suggesting a potential gain in precision diagnosis if similar benefits translate to MRI or a CT in vivo settings. Okay, and clinical decision support and personalized medicine also can be given. So that is another thing they are working on it. Quantum computerization and QML are being investigated for multiple objective treatment planning in oncology, that is radiotherapy dose optimization, integrating heterogeneous data, that is imaging, lab, geometry for patient-specific recommendation. So it is you cannot treat every patient the same way. Every patient has a different DNA and other things. What the doctors say, no, right? So how do you give a specific recommendation for that, right? So that is very much the context, the people, everything is there. So you cannot just give a general instruction, right? So to review, highlight potential for faster, more accurate risk prediction, triage, and high, that is real-time decision making in critical care once hardware and algorithm matures. Okay. Then this is another one for quantum algorithms for search, clustering, kernel methods may accelerate tasks such as variant calling, then halotype interference, integrative multinomics analysis when data sizes are huge and feature faces are high dimensionals. So they propose, the proposals include quantum enhanced pipelines that combine gene, proteins, and then transcription to derive more holistic disease signatures for precision medicine. So it is not only in healthcare. So if you see that it has in many places, like particularly in cryptography and other things. See where at one time I can go and solve, or I can go and find out what is my password, right? Instead of taking one by one, you can solve it at a time. Parallelism can be done. Okay, so many things are there, right? So this is I have just done with the thing. So what are the current limitations and challenges? So the hardware constraints are there. Today's device have limited qubit counts, short coherence time, and significant noise, that is errors, which restrict the realistic problem size and require heavy error mitigation. That is another thing. Much of the reported work still runs on simulators. See, when anybody is doing research, you cannot run on real quantum computer. We are using the QScript, okay, which is a simulator, quantum simulator, on the way on or on very small instance, or if you want to really work on IBM thing, maybe 4-bit or a maximum 5-bit or 8-bit, you can work, that do not yet outperform the best classical method at clinical relevant scales. Okay, so we are still not able to test it, whether it is outperforming the classical methods. So the current algorithmic and data issues. So encoding large medical images or high dimensional nomics data into the quantum state is non-trivial and can erase the theoretical speed up if not designed carefully. And many quantum machine learning models lack interpretability, which complicates regularity approval and clinical trust in high stakes settings. Okay, so that is another issue. So data issue and algorithmic issues. Then regulatory and ethical and workforce factors. Validation pipelines must show not only accuracy gains, but also safety, robustness across population and clear clinical benefits to satisfy complexity and cost. So there is a shortage of professionals who can simultaneously fluent in quantum technologies and biomedical or clinical domains, making multidisciplinary training crucial. So that is why, see, when you want to really test these algorithms and work on it, you should have problems to do it, right? The classical problems which we can do it will not be sufficient. So the most of the problems in networks, that is cybersecurity, and in healthcare, to my knowledge, yeah, these are the things. So for that, you should be fluent in that. Okay, multidisciplinary you should have, and you should start working on it. So with this, I'll stop my presentation. If there is any questions, I can take. So to summarize, what we have learned is the main thing. What are the properties and principles? If you see, the first one is in quantum mechanics or the quantum, the qubit, it has 3 positions. It is not 0 and 1. It is up, down, and superposition. So it is represented as a what? This one. Where is my? Yeah, it is the psi. The superposition is represented as a state vector, addition of state vectors. That is alpha get 0 plus beta get 1. Or you can say alpha 1 or alpha 2, or whatever it is. So, okay, so that is a complex numbers, then alpha square plus beta square is equal to 1. So this is how it has been represented mathematically, like addition of state vectors. And then like that, it keeps on growing. So if you have a 3-bit register, then psi becomes, so every bit, for 1 bit, it is 0 or 1. If it is 2-bit, then for 4. That is 1 by square root of 4. Then 0, 0, get 0, 0 plus 1 by square root of 4 plus 0, 1, like that. If it is 3, means it is like this, right? So the equation you can see. And yes, then the second thing is entanglement. So if I know, if I am able to measure at one part, then the other state, that is the wave or a particle on the other side, if I'm able to determine what it is, then we say that these two things are entangled. Okay, so this entangle will promote or will help or enable extremely fast correlation, and it will be having a powerful parallel computations. Okay, and the third one is the interference. Interference is what? You have to correct it. It will amplify it. One is it will amplify the correct answers by reinforcing it. Another one, it is cancelling the wrong answers. Okay, so that is called the interference. Okay, constructive and destructive. And these things are built by the qubits, is being built by Ahmad Gates, which is reversible. Okay, the gates are reversible. And then so reversible means one Adamant gate, if you connect it in two ways, from 0, it will come to 1. Or if it is 1, it is going to be 0. So it is used in succession, and it is not used as and it can be used as a NOT gate. Okay, right. Then control NOT gate is there. Yes, invert the bit into it. This is how you represent it. So h is equal to 1 by square root of 2. It has been represented as a vector thing. 1, 1, 1 minus 1. 1 and minus 1, that is the interference which will cancel it, right? So this is how, and every company or every big giants, they have their own way of implementing the hardware. Okay, so implementing the hardware which they want to replicate the mathematical thing and prove the Scontier equation and the Govers algorithm, right? So yes, so this is what we have seen, the basic principles of quantum mechanics, which can be used in quantum computing. Okay, so if you want to know more about it, you have to learn, because I think this is the first class. So you will be having a series of lectures where you will be learning the other algorithms and other things. So this is the basic of it. So we have to try to understand what it is, because as you say, no, Richard Feynman said that it is not easy to understand quantum mechanics and quantum physics and quantum computing later. Okay, if you're not bothered about how it works, but as a computer science, we can work on those things. Already it has been given. Mathematical model is available. We can implement the mathematical model through Python and SIPnet and other things, and then we can work on it. Okay, if you are a scientist only, you have to think about all those things. Already the scientist has given the models and the algorithms and the mathematical model. We can see how we can implement these models by refining our algorithms, and then we can work on it, right? So it can be used in real world problem solving. Fine. So this is what I would like to say. If there is any questions, I'm happy to answer.
Dear participants, if you have any doubt, kindly unmute yourself and ask questions or post it in the chat box.
How many people are working? Okay, if there is no questions, I'll be asking. How many people are working on quantum computing? Just type yes. Or whether it is new to you. If it is new to you, just say new. Or if you are already working on quantum computing, you say yes. Either it should be Y or N. Yes. Okay, Dr. Hemalata, yes, you are working. So what is your area, madam? Like what are you working on it? Purnima says no. Cancer research, wonderful. See, that is what for our cancer research. Nice. Okay. So you're predicting whether this person will be or what type of a cancer, like brain cancer and all other things that you are working. Breast cancer. Okay. Okay. You want to make it by using a QML, quantum machine learning algorithm, to predict it properly, right? So you are using this, yes. Fine, good. So that is where, like, we have to use quantum machine learning algorithms, machine learning to improvise. Okay, either it can be in hybrid or other things, right? Good, wonderful. For others, There was one yes and one no. What about others? To store real-time data. Fine. Real-time data. So you should be associated with some hospital, right? So wonderful. Okay. This is very basic thing. So you try to understand and try to work on it. Already, yes, ma'am. Already started collecting data with ethical. Yes, that is true. Because now data, no, the original data we need and we can work on it. Fine. All the best. Yes, maybe your research scholars must be helping you. Yeah. Is there any other questions? Okay, very base, right, must be. If it is new, you can learn. There are many things, but try as a computer science, I can say, we can learn these mathematical models and try to implement it. That will be wonderful. Instead of going why, how, and other things, it's very difficult to do it. So by implementing the mathematical model, we can work on it. Okay, then. If there is no more questions, we'll end it. Purnima, it's a beginning for you. Yes.
Yes, thank you, ma'am, for your wonderful session on quantum computing principles. Your insights have made this complex topic much easier to understand, ma'am. We appreciate your time and valuable guidance. Thank you once again, ma'am. Thank you.
Thank you. Thank you. Thank you all.
Thank you so much, ma'am. Attendance and feedback link is posted in the chat box. Participants are requested to complete it immediately. It will be available only for 15 minutes. So kindly complete the feedback and attendance. And now let's all go for a lunch break. Participants are requested to join. Sir? Is it okay, sir?
Yes, ma'am. Yes, ma'am.
Yes. Let's all go for lunch break now. Participants are requested to join back at 1:30 p.m. for the next session on foundations of distributed and federated learning. So join on time, participants. Once again, thank you so much, Malika ma'am. Thanks a lot.
Thank you for the opportunity. Thank you.
Thank you, ma'am. Thank you all.
I request all the participants to join.
A very good afternoon to everyone. Welcome back to the post-lunch session of our FDP. I hope the break has refreshed you all. Thank you for rejoining on time. We are happy to proceed with the next session, and I encourage everyone to stay connected and gain maximum benefit from the expert insights being shared today. And it is my privilege to introduce our esteemed resource person, Dr. Wenningston K, for today's session of the Faculty Development Program Quantum, where he will deliver an insightful talk on foundations of distributed and federated learning. Dr. Wenningston K received his PhD in the Department of Computer Science and Engineering from Anna University, Chennai. And he is currently working as an assistant professor in the Department of Computer Science and Engineering at NIT Srinagar. His research expertise includes computer vision and natural language processing, focusing on lightweight deep learning models for real-time edge applications in healthcare and environmental domains. His work contributes to impactful initiatives such as Swachh Bharat Mission through vision-based AI solutions. He is a recipient of the prestigious Inspire Fellowship from the Department of Science and Technology, the Government of India, and he has published more than 25 research papers, and he is actively involved in funded research projects. We are honored to have him with us today. Now, I request Dr. Wenningston K to kindly take over the session. Please, sir.
Yes, Professor, welcome.
Oh,
Sir, can you hear me?
Yes, sir. Yeah.
Yes, ma'am.
Yeah, it's audible, sir. Yes.
Yeah, thank you so much. And thank you for the introduction. And first of all, I would like to thank the organizing team for having me here as part of this faculty development program. And special thanks to Dr. Saravanan for inviting me to be part of this session. So let me share my screen.
Yes, sir.
So I hope my slides are visible.
Yes, Professor.
Yes, sir. It's visible.
Oh,
sir.
right. Okay, thank you. Okay, let's get started. And the topic of this session is going to be on foundations of distributed and federated learning. And we would understand the need for federated learning. As we all know, the machine learning and deep learning are very powerful tools for solving computational problems. So especially when it comes to prediction, a kind of supervised learning and then unsupervised learning tasks, we do have powerful models available in place. And moreover, data available for various domains are even available, which means data are mostly democratized, and even we do have access to healthcare data, financial data, and then any form of data, which means nowadays research communities now encouraged to publish their data set online so that it can be accessed by the research community. So due to the democratization of data as well as models, and then moreover, we do have no reasonable access to the high performance computing infrastructure these days. So that collectively makes any kind of computational model can be built. Right. So we'll directly get into the agenda for this session. The outline for this session is going to be the first initially we'll be talking about the challenges we have with the centralized machine learning framework, and then we would set an intuition towards federated learning, and then we would see some of the research challenges that we prevalently see in the federated learning framework. And then, if possible, we will also have discussion on some real world applications where federated learning is found to be very useful and relevant. It is not just a modern, it is more than just being a modern tool. So it has its very specific application background where federated learning is widely regarded. So that is something that we are going to focus on this talk. And then the continuation of this talk will follow on 8th of May. I have one more session on 8th of May where we'll be taking one of the serious issues or the challenges that we generally face in the federated learning frameworks, and we would explore some options, the existing options or existing solutions that people have published in the literature. That is something that we would be discussing in the second part of the series. Right. So as we all know, the standard machine learning pipeline requires certain components starting from data. So it requires data, and the data in case of training a supervised learning model. So we require data to be prepared in the form of a tabular column, something like this, where we have features x1, x2, x3, and so on and so forth up to, let's say, xn. Let this data be an n-dimensional data, and then we do have our label, which is y. Okay? So we may have some, let's say, 10,000 such records in our data. So especially when it comes to training a supervised learning model, we need to prepare data in this form. Okay? So in a generic sense, we can say that this is going to be the this indicates that the single row in the data set is actually represented by this capital X comma Y. And with the help of machine learning, and after once we have access to the data, and then we would immediately define what is the task that's supposed to be solved with the help of this data, or the fact that we wanted to basically learn from this data. And that is something I call it task here. And task could be like a prediction model, building a prediction, or what is the kind of task that we are interested in. So are we interested in, let's say, modeling a classification task? If it is a classification task, how many classification that we are targeting at? So is it a 2-class classification problem or 3-class classification problem, and so on? For example, you wanted to train a classifier in order to, let's say, recognize fruit objects from images. So we do have some finite number of fruits which are widely available, and then based on that, then we would, from the collection of data we have. So in case of, again, image data, again, you can still represent image in terms of this representation x comma y, where x part will be your image, and then the y is the corresponding label that the image carries. Okay? If the image is of, let's say, apple, then the label associated to that image is apple. If the image contains orange object in it, then it will have an associated label as orange, and so on. Likewise, you can probably consider training a model which has capability to recognize, let's say, 10 different fruit objects, or 10 different animal objects, or 10 different handwritten characters from 0 to 9. Or you can build a classifier which can recognize handwritten alphabet characters in English. Okay, including both capital and small case. Probably we are interested in, let's say, building a 52 class classification model, so which is able to recognize handwritten character in English to know any of the characters from small a to small z, and then capital A to capital Z. So something of this kind. Okay, but the task could be either, let's say, classification, or a kind of regression, or it could even be a kind of non-supervised learning algorithm as well, unsupervised learning algorithm as well. It could be kind of clustering, or any other kinds of tasks like dimensionality reduction, or sort of outlier analysis, and all such. They are the possible tasks, and the tasks are basically depends on what kind of data that we have. Okay, for example, in case we are provided only with X, then you will not be able to model any supervised learning task, because we do require label for every data point we have in our data set. Okay, so it depends on data, and you can basically determine what tasks are. It could be one or more. For every task, probably we would be focusing or targeting on targeting on building a model. Okay? And then once task is identified, then we have to choose the model. So model means the choices of machine learning algorithms we have. So for example, in case you are building a classification model, the very primary choice could be a decision tree classifier, or even k nearest neighborhood classifier, or naive Bayes, and so on and so forth, or any family of neural network classifiers, neural network based classifiers. In case of dealing with images, we could go with CNN. In case of sequence modeling, we can go with RNN, LSTM, GRUs, and so on and so forth. Okay, we have wide range of choices available for choosing model. Okay? So when I say model, we mathematically represent model as a function f that operates on input feature x, and then it gives us prediction, and that is y. So this y that we have as part of a training set is y, and the one that is predicted by the model f is going to be called y hat. So this way you can distinguish y is different from y hat. So y hat is something predicted by the model, and y is that is available as part of our data set. So now here is where the choice of model comes in. Okay, in case you go with a decision tree classifier, then the function here is decision tree algorithm, or it could be any of the neural network family of algorithm. So this is our model, and once we choose model, then we would then go with something called loss, which means this model, the chosen model, practically we would not just go with one random model, and we would generally experiment with some tens of models, and then we would choose the one that works the best for the given data. And that is the way how we basically shortlist the model. But and moreover, we do have certain strategies. So in order to try out, no, for example, when we have several options for choosing model, but we cannot practically run all possible models available for training a classifier or a regression. But we can probably initially shortlist, let's say, some 10 models to try it out. Okay. So again, we do have certain observations from various machine learning algorithms we have. So based on that, we can choose probably these are the 10 algorithms that I could experiment on this data, so that I can pick up one out of the best one out of 10 can be chosen, and that can be taken for further deployment. Okay, so that could be the way how you can set up your experiment. Okay, now you need to assess the choice of model. So in order to assess the choice of model, of course, we do have evaluation metrics where we would use some objective or subjective evaluation metrics in order to measure the performance of the model. Okay, performance of the model, when I say, it could be simply focusing on the accuracy of the model performance on unseen data. Besides that, we can also have some other characteristics of the model, which means how much memory footprint that the model requires, or the computational requirements in terms of number of operations that each model is actually performing overall. Okay, not about training most importantly. Most importantly, we care about the number of operations performed during the testing time. Okay, during the inference time. Okay, at the inference time, what are the resource what are the resource expectations of the model? Okay? This is one way we can still analyze the performance, considering the hardware factors, like it depends on the choice of your deployment options. You can even measure these aspects of the model. Right. But that is going to give us some insights about model, not some insights. It gives us overall idea about the model or the performance of the model. But the reason why we need to assess loss is that the learning algorithm that your function f will be using is going to be guided by this loss function. Okay, so the learning algorithm is generally being guided by the loss function. Okay, loss is going to be measured in terms of kind of it is going to be, because loss value is generally not interpretable. But yes, of course, as we all know, since we are assessing loss here, loss of the model or the error of the model or the cost of the model, the cost of the model or the loss or error of the model is generally expected to be as minimum as possible, and the ideal loss value is going to be 0. Okay, but as of course, it's going to be an aggregate, because model is going to be basically approximated with the number of samples you have in the training set. So that model is going to be aggregated based on set of some large number of instances, right? Since it's going to be a kind of approximation over some thousands of data points, so it's very difficult to expect a model to report probably a loss close to 0 is something which we can expect, but reporting a loss of a model that is exactly equal to 0 is something that is not feasible in most of the real world applications. right? So now the way how loss is going to be assessed is that right during the training process, and we would evaluate. No, we do have we have decided the algorithm to test, let's say, some family of neural network algorithm. And as we all know, neural network involves a lot of parameters because neural network models are generally considered very complex compared to other classic machine learning algorithms like SVM or naive Bayes or decision tree or KNN kind of classifiers. Okay, where the number of parameters are going to be very less and not very high. But when it comes to neural network family, we do have adequate flexibility to tune the model, fine tune the model, or exploring in case if we find that the chosen neural network model is not adequately complex for fitting the given data. So we can very easily we can increase the complexity of the model by adding, let's say, one more hidden layer to it, or increase the number of neurons. In case we wanted to probably reduce the complexity of model, we can still work on the number of neurons in each layer, and then we can consider, let's say, eliminating one or few of the hidden layers from the existing architecture. Okay, we do have that flexibility, and even rest of our discussion will be based on the neural network kind of architecture, where we are going to practically deal with several millions of parameters. Right. So now we have decided the architectural configuration for a neural network model, which means what are the number of neurons in the first hidden layer, how many hidden layers, how many neurons in the output layer, and what activation function are we going to use, right? And what other internal mechanisms like regularization and other factors like there's dropout factor, and then many others, right? So let us assume that we go with an initial or the standard configuration for any fully connected neural network model. Okay, so now that neural network function model will act as this function f, and now this chosen neural network model in the very first step, so it will pass through all the instances in the training set. Okay, now we have assumed that there are 10,000 instances in our training set. So now this model will go through all the data points from the training set. Okay, so there are 10,000 data points here. So now the chosen model in the very first step, so it is going to go through all the data points in the training set, and then let us again go with a simple binary class classification task, so that for all the 10,000 instances we have associated label. And now after going through all the data points in the model, let us assume that function f, the chosen neural network model, has, let's say, classified 8K data points correctly while making error on remaining 2K instances. So which means now we can say that probably model is working with accuracy of 80%, and that's not the right way basically to comment on the performance of the model at this stage, as model is now in a very preliminary stage and it has not yet matured, right? So because model will mature, which means model will learn right set of parameters no, only when it go through the data instances, training data instances, multiple times over and again. That is what we call epoch in any standard neural network training, right? So now model is actually underperforming on or reporting error on remaining 2,000 instances out of 10,000 training instances, and now this will accumulate some quantity of the loss. Okay, for example, for all the 10K points, we have this Y part associated label, and then the Y dash, let's say Y cap is, let's say for true label is something 1. Y is actually equal to 1, let's say for a data instance D1. Okay, D1. And then the model has, let's say, predicted for the data instance D1 as, let's say, um, 0. So which means no, instead of predicting its correct label, that is 1, model has mistakenly predicted it as 0, which means it's an error. So this error will basically accumulate and then accumulate the loss. And then loss is some numeric quantity. Now that will define how bad model is performing for the current parameter setting. Okay? So that information is going to be shared with the learning algorithm, and learning algorithm is also called as an optimization algorithm. So because training a neural network model is basically an optimization problem where we are interested in minimizing the amount of loss. So it is going to be a kind of minimization algorithm. So we wanted to identify the right parameter of the model. I use the notation theta here in order to define the parameters of the model. Okay, I use this theta here. I use theta in order to. So in case any disruption in the line, so please let me know.
Yes, sir. Yes.
Thank you. Thank you.
Yes.
Right. So theta is generally the notation we use for the parameters of the model. As we all know, in neural network, as every neurons are basically interconnected, at least at the layer level, so that every connection in the neural network actually corresponds to a parameter. Okay, so that parameter is what I'm talking about. So initially, we would start with some sort of random initialized values for these parameters. And then in the very for the randomly chosen set of parameters, and we assess the loss, and then that information is going to be provided to the learning algorithm in turn to the optimization algorithm. We do have various optimization algorithms such as Adam optimizer, Adagrad, RMS prog, and then probably the vanilla gradient descent, and then gradient descent again comes in various forms like momentum based gradient descent, accelerated gradient descent, and then there are many variants. There are several hundreds of optimizers available for training neural network in an efficient way. Okay? But these are generally the primary choices, and if you go with the standard neural network setting, I think one of these algorithms would be by default chosen by Python library, whatsoever you use. Okay, so now this algorithm will take some insights from loss, and then it would revise the parameters. As it is a minimization problem, these optimizers are expected to minimize or alter the parameters of the model in such a way that the loss of the model will be declining over time. Okay, so whatever loss is reported in the previous step is expected to be reduced in the subsequent steps. So that is the idea with which these optimizers will cleverly, because we know that generally of course, let me not talk about the range of values for parameters. Parameter value could be any real value generally. Okay, and if you look at the domain of real numbers, and we do have no uncountable, no, it is infinite, of course. And moreover, any infinite quantity can't be counted, but it is a special kind of real domain where the number of parameters are infinite as well as uncountable, right? So we can't even count the number of real numbers between, let's say, 1 and 2, or even 0 to 1. Okay, so for example, 0 to 0.01 could be a real number lying between 0 and 1, and so on and so forth. Okay? We find infinitely many no real numbers between 0 and 1. Okay, so when we consider, let's say, the integer numbers or positive integer numbers, let's say from a positive or negative, inclusive both, minus n to, let's say, 0, and then from 0 to n, it is still infinite, but it is something that is actually countable. So don't get into all these characteristics for now, but just this may probably help us in understanding certain things later. Right? When it is a collection of let's say n positive or positive or negative integers, and it is going to be countable. But on the other hand, the real real domain is quite complex, and the number of real possible real values between a very small ranges itself is uncountable, uncountably infinite. So now these algorithms cannot now work at random. So it cannot again randomly change the parameters of the model. In case if it randomly changes the parameters of the model, then again it may lead to the challenge that model may probably take more iterations or more steps in order to converge with the right set of parameters. Okay, instead of model taking 50 steps to learn right set of parameters of the model, probably model could end up running, let's say, 5,000 plus epochs, 5,000 step iterations, and then finally it is identifying. Okay, so it again adds a lot of overhead and then cost to the training process. Okay, sometimes in some resource constraint setting, and we may not be able to afford to run 5,000 epochs or 10,000 epochs in order to learn right set of parameters. Okay, always lesser is the best. Or if you could learn right set of parameters in less iterations, it is always good and then preferred. Okay. So now, accordingly, yes, this optimizers will have an objective that it's supposed to guess or suggest or update weights or the parameters in such a way that it actually um, uh, you know, uh, uh, guess or fix or learn the right set of parameters for the model. So that how do we know that these are the parameters which are right for the chosen model? That is going to be indicated by loss. So through loss, it is revealed that these are the right set of parameters of the model, because we know that the loss is expected to be something close to zero. Okay, that's how learning algorithm is going to run in an iterative fashion, so that it will be over and again running on the training instances so as to report loss at the end of every iteration. And then at one point in time, in case we are not able to reduce loss any further, then that could be probably an indicator where you can stop the learning process, or you can also designate let's say the number of epochs or number of iterations that I'm going to run are going to be 100. So you can run learning algorithm for 100 steps, or even you can decide it to 200 steps, 300 steps, and so on. That number is basically a hyperparameter, and that doesn't that is not relevant to the training set, but it is something that you can decide based on the experimental settings. Okay, you can consider it as an hyperparameter so that you can run learning algorithm, let's say, for 50 steps, 50 iterations, 100 iterations, 200 iterations, 300 iterations, and then observe what is going to be the ideal number of steps required or iterations required for learning parameters for the given model with the help of given loss function and then the optimizer. Okay? So that would again differ. If you use another optimizer, probably that would take maybe more than the other algorithm, more number of steps than the other algorithm, or less than the other algorithm. Okay, so it could be possible because every optimizer has its own characteristics in order to learn the parameters. Okay, and then once we learn right set of parameters of the model for which the loss quantity is minimum or acceptable, because the ideal loss is something zero. But again, that is our primary optimization problem. But again, getting into the best, loss is not always guaranteed in this kind of approximation setting. But that's why we restrict it to, let's say, some value which is close to zero is something which is practically, feasible and then relevant. So when once such condition is arrived, then we can then take the model for evaluation. The sixth step is going to be evaluation, where the standard evaluation metrics or performance indicators, like precision, recall, accuracy, and all such metrics are going to be used in order to evaluate the overall model. Once it is satisfactory, then the model can be taken for deployment. And this is standard machine learning pipeline or even neural network pipeline. And this is what basically happens end to end in any life cycle that involves machine learning based solution. Okay. So now if you observe the way we do the training process, which means the major work contributed by the optimizer or the learning algorithm is something called as learning. So what essentially we are learning is, as of course, the learning of parameters are happening, and it is based on the data that we have at hand. It is based on the parameters are going to be learned based on what data that we use for training. Okay, so the training instances we use for the model to learn the right set of parameters. Okay, that is why actually we call it actually a learning. So learning where actually model is attempting, or the overall pipeline is attempting, or the learning algorithm is attempting to learn right set of parameters of the model. Okay, so now you can sorry. So you can assume that these types of operations are basically done in a centralized manner. So which means you have your data readily available in the system let's say you have your workstation or kind of high performance computing infrastructure. So where because when I say data, the data could again vary, right? Right from probably 10,000 K instances all the way up to, let's say, 10 million instances. The number of instances could be anything. And again, number of features could be, let's say, ranging from 100 to again 1 million. Okay? It could be anything because accordingly, as the size of the data set increases and the complexity lies with the data set also increases. Okay. So accordingly, depends on what size of data that you are working with, and you require adequate hardware resources or the computing resources in place, which is centrally available, which means you should be able to load the data that you have in the centralized computer where both data as well as your model will be residing, and then model will be referencing data as and when required in the process of learning parameters. Okay, so that is what the centralized training is all about, which means where in the case of centralized training, both data set as well as model runs in the same workstation or high performance computing. Okay. So on the other hand, we have something called as distributed training. Okay, maybe before getting into that, let us just quickly go through what are the challenges we face when it comes to centralized training. Okay, which means the standard pipeline of machine learning model. Okay. So first of all data has to be available in a single server or a central cluster. It could even be a clusters of computer, but you have a high performance clusters where you have, let's say, integrated, let's say, hundreds of commodity computers or hundreds of workstations together to have a central cluster where data is supposed to be residing. Okay, so this actually leads to the data privacy issues. For example, you wanted to, let's say, learn no learn about let's say a pandemic. Okay, so we all have, most of us have experienced, and all of us have experienced rather, right, experienced the COVID pandemic, right? So that was in peak, in 2020, 2021. During that time, right now, hospitals were rushing, with patients, and patients were visiting hospitals for treatment, and then hospitals were able to generate, let's say, a lot of data about patients who are visiting with COVID symptoms, without COVID symptoms, and with symptoms diagnosed with COVID, and without symptoms diagnosed with COVID, and so on. Right? There are a lot of varieties of, and there are people who are diagnosed with some symptoms of COVID, but it is not COVID, and maybe some other viral infection, something like that. Okay, they've been collecting a lot of data at every hospital unit. Right now, let's say we wanted to basically make use of all this data in order to learn a model, and that model can in turn be used for diagnosing COVID infection. It's a simple task. You can find out hundreds of tasks in this pandemic data set, right? One simple task is about predicting or diagnosing the health condition in the in connection to COVID-19. Okay, you can probably fairly define few reasonable categories. One is probably the no COVID case. The other one is COVID probably with symptoms, COVID without symptoms, or it could be a kind of other viral flu which is not COVID. Okay, likewise, you can define some sort of standard, and then you wanted to actually gather data from data across the country, and then you wanted to train a holistic or comprehensive model that can work in diagnosing COVID in an efficient way. Let's say this is our target we have. So now data lies with the different hospitals across the country or the state. Where there are, let's say, hundreds of hospitals, hospital units, or thousands of hospital units, data are collected at every hospital, and let's say it is initially kept in the local servers at every hospital units. Okay? So now, in case you wanted to train a model from data across these local sites, first of all, we need to basically move data from different local sites, different hospital units, and onto a central server, right? A central single server. So that is something that is needed. During this transit time, of course, the privacy of the data could be leaked. Some unauthorized users may gain access over your data, so that data gets leaked, right? The private no private patient data gets leaked. It's a severe threat, and no government or even no individual will generally allow this to happen. right? So that is a severe issue called data privacy issue. And then and that is the reason basically why we are going towards federated learning. So there are some interesting use cases of this. No, there are different use cases where the centralized training is basically not suggested. For example, the auto correction for smartphone keyboards. So if there is a machine learning algorithm running in your mobile phone or in your electronic devices, whatsoever you use, and you auto correction is something that is a generic auto correction is not something that I'm talking about, because in order to learn a generic auto correction, probably we would require data from the keyboard typing information from different users so as to train a central model, and then the model at the local device or the mobile device must be updated, right? That is what the requirement. But what is being done currently is that, so take the keyboard typing pattern of the individual user, so that try to change the model locally within the site, okay, without requiring without required without the need of sending data all the way to server. Likewise, many users who are using that particular, probably some text kind of messenger app where typing is a primary operation. So a central model, in order to get updated, it requires feedback from, let's say, all the mobile users who are using that particular app. Okay? So that is going to lead to a lot of overhead at the central server side. Okay, and moreover, there will be a lot of bias because the majority of people, if they follow some kind of auto correction mechanism, then that feedback would basically be biasing the overall model, that is actually going to be circulated or distributed across the where all the distributed across the mobile phone users. Okay? So instead of doing that, and we can basically fine tune the local machine learning model, and that can work based on the feedback of my own typing pattern, so that no need to basically share my private typing pattern information with a central server, because on transit anything can happen and my typing pattern could be understood by anybody. Okay, they can probably try to learn what kind of typing pattern I have, so that they may try to understand some of my behavioral signals. Okay, that is something that I wanted to prevent. Okay? So even if this application is a very small scale application, the utility of this auto correction is a very small, compared to other many gigantic applications we have around, especially from the medical domain. So medical records, generally distributed across different hospitals, because every hospitals have different patient group, the patient community, and then as and when they visit hospital, and then they generate a lot of data, and then they keep it centrally available. Okay, so now when it comes to building a model or training a model in a centralized manner, all this data must be gathered in a central server, right? So that actually lead to severe privacy threat. Okay, or the other way is, so the other way is that even you can share the gradient loss, the loss which I have meant here, right? So in case we also call it a kind of, we also call it a gradient loss. Okay? Gradient loss and loss or error or all can be interchangeably used. So now let us say that you decided to train the model in a distributed fashion. So I have a diagram here to explain you what is the distributed way of training the model. So this is something that the standard machine learning pipeline is. Okay, this is basically the standard ML pipeline, where first gather data from different sites. There are some data coming from mobile phones, some from, let's say, sensors in car, some data from sensors fixed in smart home, and then all these data are actually pushed to cloud. And then where you have high performance cloud, high performance compute cloud, as well as storage cloud, so that you can safely store all the data in one place, and then you can run model on that data. So that is the centralized approach. On the other hand, we have this distributed approach where wherever data are, run the model. Okay, which means you have some data here residing in smart home, and then some data residing in your car itself, and then there's some information, some data available in your mobile phone, right? Okay, so it could be any signal. Just take it in general. So data are available. So you run probably the model straight away in these devices. So it's again a kind of challenge we have, because the heavy model that you can run here in a smart home setting may not be applicable here in the mobile setting. Okay, but anyhow, nowadays mobile is none other than a computer, right? No longer even a mini computer, and mobile has fairly good infrastructure, fairly good configuration, and then the configuration of mobile phones are are on par with specification or the configuration of personal computer. But still, it is a miniature device, and then it is running lot of applications in parallel, because there are a lot of 24/7 apps are basically running in mobile phone. That may probably lead to a kind of overhead, running a training algorithm on mobile phone directly. It may even heat it up, okay, because it is a battery powered device, and then probably when model training is happening in mobile phone, probably it would consume enormous energy, and then battery would get drained very quickly. And these are some of the other challenges besides the as such specification limitations, right? And then again, you will have a different hardware infrastructure, let's say for processing smart car, a smart vehicle, or driverless car kind of application, or smart car, where it senses some information when you are operating a vehicle. So whether your health condition is right, or the car health of the car itself is okay, to have a long ride or a short ride, and how is the condition of the car, all such things. Okay, you can think about all this, right? You can play every vehicle, every electronic, every mechanical um, equipment now comes with several inbuilt sensors, and all of them are basically collecting a lot of data about environment and about working condition of a machine, and then all that can be basically finally consolidated for learning from, or we can learn some interesting hidden patterns out of it. Yeah, right. So in a distributed algorithm, a model is going to be dedicatedly running in the place in the device where data are available. Okay, that is distributed, and then finally, of course, as long as these models are same, and you can combine them. So you can combine them. For example, this is the model where, let's say, 10 million parameters are involved. I think 10 million is a big number. Anyhow, for example, okay, let it be 10,000. And again, this is again it's a similar model running on 10 million parameters. And this is again a 10 million parameter model. And now we got three 10 million set of parameters for each of these different distributed models. And now how can we then combine all these models into just one? Okay, we can again aggregate them, right? So instead of using, let's say, first parameter from this model, or from this model, or from this model, you can, of course, choose to do it. Of course, because there are various ways we can aggregate these weights of distributed model. But besides that, what you can also do is that you can simply take an average weight, or average parameter value of all the first parameter, and then similarly you can do the same kind of aggregation for all the remaining parameters of the model. That is something. Or you can also use this model, whatever learned from the local device, and you can use this model as part of this app itself without even aggregation. That can also be done. That's a kind of distributed approach. So even when you share the model after learning is locally done on the data set, even when you attempt to share the model with others, you will be sharing the model in terms of set of weights. Okay, the model F is no longer this, as good as simply the set of parameters that this model involves, which are learned from F. Okay, right? So now there are potential attacks possible straight away on this theta parameter. So even by learning, or by understanding, or by decoding the parameters of the model, one can even attempt to generate the input sample. Okay, which means in case of healthcare setting, input is nothing but our health records. Okay, so inputs are nothing but health records of patients, And now if you could reconstruct this health record with the help of this data, it is something that must be prevented. Then that is another challenge we have when it comes to centralized training. So in case you have completed your training centrally in a local system or in a local system or in a cloud kind of environment or a HPC kind of environment, and when you share the model in terms of gradient loss alone or the amount of loss that is incurring at every step, or it's not just the parameters again, because again reconstructing data from parameters is again a research area, mostly on the security of the model. Okay, it's something called as adversarial attacks and all that. It is a separate field in the world of machine learning, and where people are trying to reconstruct training samples from parameters. But it might be quite difficult. Uh, but but reconstructing data from the gradient loss. Gradient loss is something that we are measuring at every iteration, right? So generally that gets stored in a kind of log or in kind of history while training the model. Even if you could have access to this gradient loss, that can lead to a severe problem of revealing the actual training instance. Okay, again, any training instance is not going to be more valuable, but when it comes to healthcare or kind of sensitive financial information, of course, it's going to be a big threat. And moreover, the parameter server is good for cloud data centers, so but very poor for wide area distributed devices. For example, you cannot keep everything central, right? Because there are mobile applications which are running on every mobile phone, right? Any email box or email inbox or any other messenger kind of applications which are predominantly seen in almost every mobile phone nowadays. Even by default there are some hundreds of applications coming. Just update OS and then you get some hundreds of updates to various applications running on top of it. Okay, so now gathering data from all the mobile users and then running the model centrally at one side and then again broadcasting this updated model to all the mobile devices. So it leads to a lot of challenges, and that is what all that we have seen here. And that's where the notion of distributed approach comes in. And then again, distributed approach has this architecture. So the wherever data are located, and we are going to run models straight away on those data instances. Okay. On the other hand, the federated learning, in which what we're going to do is we are going to have a global model. So we are going to have a central node where we'll have our global model. And then this global model, the copy of global model, will also be running in respective local sites. For example, the copy of global model is no different from the local model. And when I say from the architecture level, from the neural network model level or the machine learning model level, the global model is no different from the local model which are running here. Okay? But where the data are, and this model is going to be learning parameters from the data that we have in this various local sites. And then finally, the aggregation is something which is optional in the case of distributed approach, but it is mandatory in the case of federated learning, because we wanted to have a collective picture, right? Again, coming back to our COVID scenario, COVID use case, where we wanted to build a diagnostic model comprising data from different hospital units across the country or the state. Right? Imagine now how much amount of data that we are looking for, right? So now instead of actually moving all the data to a central server, better that we send model to the local sites. Okay, so the model, the global model, a copy of global model is going to be sent to all the local sites, and then let the training happens there in every rounds. Okay, as per the designated number of, let's say, iterations, 50 or 100. And on completion of every iteration at the local site, the model parameters are going to be shared with the central node or the global model. So global model will then aggregate the parameters learned by different local models running across different devices are going to be aggregated based on some principle. Okay, a simple one could be a direct average, right? Because all the models are same, so the number of parameters are same. So this the model running in this device will have an update for, let's say, one of the weights. Similarly, for the same weight, and this is since it is learning from a different copy of data, different copy of not same data, right? It is completely a different population, right? Different sample space, right? Similarly, this model is running on different sample space, and then it would recommend some change to parameter one. This would recommend some change to parameter one. This would again recommend something to parameter one. And now, how can central model take update or the feedback from each of these local models? Yeah. Again, the straightforward aggregation model will work this way. Simply take an average of these three value and make it a actual value for the global model. And once this process is completely done, then the model will again be broadcast to all the local sites for second iteration. Okay. So now for second iteration, a copy of global model is going to be sent to all the local devices, so that again the next step of the iteration can be executed by the local model, and then again it would recommend some changes to the parameters. It would again share it with the central node, and then central node will again combine based on the aggregation logic, and then it will again share the updated global model with all the local models, all the local devices, and then this operation will be repeatedly happening. As you look at it from the high level point of view, and you would find out lot of overheads involved here in terms of communication overhead, in terms of computational overhead, and then in terms of kind of data exchange, frequent data exchange happening between central node and the various local sites or the local sites. Okay? Right. So of course, and that actually paves way for optimization or the improvement of federated training setting or federated learning setting. Okay. Right. Right. So now, since the distributedness is seen in both federated training as well as in the distributed training, um, so the reason why we actually go for the distributed training is that due to the model size. Okay? Let's say that so a model sometimes would require several partial local trainings, and moreover model do not fit in memory and hence needed to be trained in part in a distributed setting. Okay, so for example, you have to, let's say, run model only on the piece of data available at this local device. Okay, so and then probably you can combine them based on some sort of aggregation method. Okay? And then moreover, data itself is not centralized, and then again bringing data in a central location is again challenging, right? It again causes this privacy issue. So we are forced to actually run models straight away on data. So these are certain requirements that actually enable us move from standard machine learning training to federated machine learning or federated learning in general. Yeah. So federated learning is a machine learning paradigm, so where a model is trained across multiple decentralized devices. So usually in most of the cases, it could it could be running in decentralized powerful servers like this, as well as it can even run on some local devices which are very lightweight in nature, which are also called as edge devices. So for example, it could be a mobile device, it could be a mobile device, or it could be a kind of edge accelerator. So edge accelerators, or even some sort of sensors or kind of microcontrollers. Okay, when you're trying to learn from data collected by these devices in itself, in the device itself, let's say mobile generates a lot of data. So why should we transfer data from mobile to, let's say, central server, central cloud in order to do some learning on top of it? Okay, why don't you run directly model in the mobile device itself, let it learn, or let it at least update the local knowledge that it can gain from the locally generated data over time. Okay. Similarly, there are sensors which are autonomous generally, and sensors are generally observing the environment and collecting data. So earlier sensors were just seen as a data collecting agent, right? It just participates only in data collection, and then it sends data, collects from environment and then send it to the server. And then server where the aggregation will takes place from multiple sensors, and then data will be prepared for training machine learning model. So why don't sensors run some small model in itself? Okay, for example, you can think of running, let's say, a model straight away on drones. The drone has a lot of sensors, and then whatever data the drone collects, and let the model be executed straight away on drone itself, right? I'm not talking about training model on drone. I'm talking about at least doing the inference part, okay, the diagnosis part. Okay, drone collects some information, let the machine learning model be running on drone, which can take inputs from various sensors and then do some predictive analytics straight away on board. And that is the idea. Similarly, you can think of making it more intelligent, making the CCTV cameras more intelligent by enabling a model running in the CCTV itself, right? So let it not just be a vision system which just looks at and then record the video or record the frames in the local computer. Let it also run some small AI model so that it can even predict, is the one seen in the camera is intruder or the one who is authenticated to be authorized one to move around the locality. Yeah, something of that kind. So there are a lot of applications where the devices, when I say, I mean inclusive of all, not just the workstation level, workstation grade devices. It can even be a lightweight devices like these microcontroller sensors or even edge accelerators, mobile devices, and so on. Okay. So actually here the raw data exchange is not required, so that to some extent the privacy of data could be preserved, and only model weights, the gradients or the weight updates. The gradients or weight updates are only shared with the central storage. But of course, it again leads to a threat. Okay, as we have seen before, it is a severe problem, right? Okay, just by gathering gradient, which is transmitted from local system to central server, at the end of every epoch, if someone gains access to this gradient loss information, okay, and probably passively the attacker may be observing this gradient pattern and then try to reconstruct the original data point. Yes, of course, it is also possible, and yes, this research area is also being widely popular, and a lot of proposals we see in the literature. And then, the key idea behind federated learning is that let the data stay locally, and then let the model run locally, and then only the updates are actually shared with the central server. And then that's what the second point is. Actually, even computation can happen distributedly, and then once the computation or the learning of parameter process is done, then data can be shared with the central server. And again, central server will then collect information from all the local sites, and then it will come up with an aggregated model, and then the aggregated model will then be again distributed or shared with all the local participating nodes, and then again it will run respective second iteration at all the local stations, and then it will share the data back to the global model, and then for aggregation. This will continue until no, the global model is built from the local copies which are residing distributedly across various sites. Okay, so this way we can probably build a diagnostic model for, let's say, COVID prediction, which has gained knowledge across data available across various hospital units in the state. Okay, so that is the overall idea we have under this federated learning, and there are a lot of questions we have at this moment. Okay, so one is, what is the principle are we going to use in order to combine the copies of local model in order to get a single global model? Okay, the way we aggregate, and that aggregation part is what will be covered in the next part of this lecture series, especially by me on 8th of May. But for now, let us have a very high level view of what aggregation and how it can be basically done. Okay? And then besides that, should we really wait for all the clients to respond? Okay. For example, as you have observed in the previous architecture, there is one device which is running in car, one device which is running in house, one is running in mobile phone. Okay, so there we see lot of diversity in hardware, right? So not all hardwares are same. Again, in a hospital setting, yes, if it is a district hospital, probably it would have good infrastructure. Or if there is a hospital which is located in a state capital, will be very much equipped in terms of both infrastructure as well as hardware. And what about the primary healthcare centers which are located in a small town or in a village? Okay, so probably they may not have adequate infrastructure, right? So what can happen here is that it is very difficult for the global model to wait till the local model completes its updates. Okay, for example, other participating high level entities like a district hospital, a hospital located in a district headquarters, and a hospital located in a state headquarters will have adequate resources so that it can run local training so fast and it can respond to global model very quickly. So compared to other small medical units like primary or tertiary, kind of secondary healthcare centers or tertiary healthcare centers, kind of systems cannot respond as quickly as the major participating local sites, especially like hospitals at district headquarters and then state headquarters. So these are some of the challenges. So should the global model be really waiting, till every participating primary healthcare centers are actually sending their updates? Okay, so meantime, prior PHCs are still doing some computations. By the time the main big hospitals would have already shared the update with the global model, and now while PHCs are doing some computations, the other big hospitals have already sent us the update and they have gone into an idle mode. Because that idleness is something that we hate. Okay. And again, updates from even PHCs are also important, okay, because we are learning a global model. We can't simply rule out all the PHCs just because the number of patients visiting PHCs are less, and then again they are taking more time, in order to update us with respective updates or the parameter updates that they have learned from those locality, patients, who are locally available. Okay, but especially considering other hospitals like the district hospital or the state headquarters hospital, where the people from entire part of the state or entire part of the district would generally be visiting there, and the notion of local behavior about a particular pandemic can't be basically learned from these data sets. Okay, so what I'm trying to say here is we have no proper grounds in order to rule out the local updates just because it is coming from PHC, where where there are only 50 patients visiting per day related to COVID. Okay? So that is not the factor with which we can rule out the PHC, so chosen PHC. Okay? So everything is equally important. So how can we handle that case? And again, our updates from all the local sites are really important. On the other hand, okay, especially for modeling a COVID kind of pandemic. So as mostly the district hospital itself handles patients from wide locality, right? Locality across the district boundary. So that why should we really depend on PHC? I can give various justifications whether should I include PHCs into learning process or should I rule out from should I ignore them from participating in training process? Okay, I have a lot of such questions, and these are really the practical challenges we have. And then people have come up with various proposals now how we can go about client selection, especially the sensors are very less reliable devices, right? Sensors generally are less reliable because they prone to various attacks, right? Sometimes sensor readings may go wrong. So initially at the time of deployment, it may be working right, and then over time, it may get degraded due to probably external factors like probably rain may affect sensors. If they are not water resistant, probably it would get affected by rain, water, and then if they are not temperature resistant, again due to high temperature or even low temperature, sensors may start malfunctioning. Okay, again why should we really believe in sensor data? So whatsoever model parameters that are learned from such erroneous data should be included in global model update. Okay, these are some of the challenges, questions we have. Is of course the answer to these questions would even differ domain to domain. Okay, maybe we don't have a concrete or a kind of a very decisive answer for all these questions. Again, it depends on what kind of data that you're dealing with, what kind of task that you're dealing with, and what kind of domain that you're dealing with. Okay, where the error or the participation of the local sites can probably be handled in a graceful manner. Okay, right. Right. So let us now try to understand more technically. So what happens in each round of training in a federated setting, in a federated learning? So if there are any questions in the chat window, or if you have any questions, and maybe I can pause for a while, you can.
Stay participants, if you have any questions, please ask. Sir is here for clarifying your doubt. Please, if you have any questions or clarifications about this session, please ask the question. Or if you want, you post that doubts on chat box itself, not a problem.
Yeah, it is again fine. Yes.
Yes. Please unmute yourself. And if you have any questions or clarification, sir is waiting here for clarify your doubts. Please.
So anything is fine. If you need time,
Yeah.
we can even consolidate. We can
Yes,
we
sir.
can
And
have
otherwise,
question
you will
answers
note
at the
it
end.
down.
Yes,
At
yes.
the end of presentation session also, we'll discuss about your doubts. Yes.
Sure, sure.
Yeah.
Okay.
Thank you, sir.
Okay, thank you.
Yes, sir. Thank you, sir.
Okay, so let us now understand. So far we have just built an intuition of why federated learning setting is required. Okay, though we have data available across, and then computational requirements we have, which means we have good workstation access to good workstation, and then in some cases we do have access to HPC resources, and then free cloud resources are available, and then the libraries are available. So Python libraries are freely available now. Right? So without even citing them, without even paying them anything, we still have access to all these resources, right? And that's why we see that lot of research works are being coming out, exercising with a lot of machine learning, deep learning frameworks. Right. So let us understand, what is happening at each round. Okay, probably I can come back to this slide after looking at this diagram. For example, so this is what basically happens in each round of training. Okay? We do have a central server.
Excuse me, sir.
Yeah, and then
Hello.
yes, yes.
So I just wanted to share my thoughts on my research, current research, which I'm doing, sir, on federated learning.
Right.
We are actually trying to do a research based on organ matching.
Okay.
And transplantation of system using federated learning and deep survival prediction framework.
Okay.
So your input today on federated learning was quite useful, sir. Just wanted to share it.
Sure. It is really an interesting problem. Probably you can at the end of the talk, probably you can describe what is the actual problem statement that you're addressing, and let us definitely analyze the suitability of federated learning in your application.
Okay.
Yes,
Sure.
certainly.
Thank you.
Yeah.
Thank you.
Thank you. Because it also depends on what kind of data available to you and what are going to be the participating local sites. Accordingly, actually, we have various choices to make at the various parts of the federated learning framework. We can discuss it at the end of the talk. Yes, sure.
Okay, thank you, sir.
Thank you. Right. So this is what happens at every round in the training process in a federated setting. We have a central server where we decide the global model. Okay? As you can see here, initially the global model, which means global model, when I say this global model is your function f, right? It is your function f. It could be a kind of neural network model, and that model, and every model will also have a set of parameters theta, right? So we initialize the parameters theta for a global model, and then we send it to all the local sites. There are 4 local sites here. One is here. This is one of the local, maybe I can use different numbering. So this is local site 1, and this is local site 2, this is local site 3, and this is local site 4. There are 4 devices which are participating in this local training process. Okay, so you can associate this architecture to any of the domains of your choice. Okay, in case of a healthcare setting, probably the central server is going to have a capability to handle send and receive things that are happening in this overall pipeline. The local centers are like the hospitals located in, let's say, rural village. So for now, let us assume that all the local participating sites are almost like a homogeneous collection of local sites. Okay, which means I just consider only the PHCs located in rural villages, or primary healthcare centers located in urban areas. Okay? So like the way we can even limit it. That is what the choice of problem that we have, or the problem intent that we are looking to address. Based on that, we can actually do some workout on carving this architectural design. Okay? Maybe here we can for now assume that all the devices, or the edge devices, or all the devices in the local sites are almost having similar configuration, so that we can have them as a kind of homogeneous collection of local sites. Okay? So once after receiving the copy of parameters of the global model, it can the local model will then initiate the training. So the local model training is actually happening on the local data, because in case of federated setting, we wanted to ensure privacy. So we don't allow data to be directly transferred to the central server. So instead of transferring data directly to the central server in a federated setting, and only the model parameters which are learned from the local copy of data are shared with the central server. And so that is the idea here. But it is still, it has a threat of even decoding. Someone may even attempt to decode the original data that were used in training, let's say, the particular local model. Okay, that is also possible, but yes, of course, that research is still under research, and then yeah, it is maturing over time. And appropriately, on the other hand, again, federated learning framework is also adding a lot of security related, privacy related mechanisms, so as to break that challenge. Right. So here is the model. Okay, this is the global model we have, and as you can see here visually, right, the same copy of same copy of global model is shared with all the local sites, and they are now called local model. And then the training of this model is being done on the local copy we have here at every site, and that is happening. So once it is done, then every participating site actually sends the gradient update to the central server. Okay, so when I use this delta notation, actually that indicates that the gradient information. Okay, that is basically the rate of change, right? Say for example, for all the weights, let's say from W1 all the way up to, let's say, WN, where n may be a very big number, like n may be like probably 1 million or 2 million or 3 million, any number of parameters. And for every weight, it actually shares only the rate of change or the amount of change. For example, W1 supposed to be, let's say, added with some quantity 0.01. And for W2, some value, let's say 0.007 must be negated. Okay, this is what delta is all about. Okay, so that gradient information is actually sent to the local server by all the local sites. So all the local sites are also doing the same thing. Okay, for here we are indicating, maybe W1 indicate that it is the gradient information from local site 1. Okay, maybe if I add one more superscript 1, that indicates that this is the first parameter of the model from first participating local site. Okay, and then probably this should be 1,2, which means, again, you can have appropriate superscripting in order to denote which weight are we talking about. Okay, in case we are interested in even showing weight of the weights involved in different hidden layers in the neural network model. Okay, so that can also be indicated. You can again add one more superscript to it in order to indicate that this indicates that from the first local site, and then from the first hidden layer, and this is the first weight, and then from the first hidden layer, this is the second weight, and so on and so forth. Okay, you can have different interpretations for it as you get deeper into this learning process in the federated setting. So this happens after the end of first round of learning that happens distributedly in each local copy of data with a copy of global model. Okay, so once the gradient updates are shared with the central server, so central server will then go for updating the global model, because initially it just initialized. Initially it had one DJ, right? Right. So then the central server uses simple aggregation mechanism. It takes the gradient information from all the local sites, and then it simply takes an average of each weight, and then it is going to update all the parameters involved in the model. All the parameters involved in the model are updated based on the aggregate knowledge that it has gained from different locally participating agent. Okay, and this formulation could differ from one federated learning architecture to other. Okay? So here I go with a very simple averaging mechanism, and we can even go for kind of weighted averaging also. And again, how do we determine weighting? Again, you can determine it based on various other factors. Okay. So you can go with even weighted averaging. So weighted averaging in the sense, let's say in this local site, let's say the number of data instances are, let's say 10K. And in this local site, let's say number of instances are only 2K. And in this local site, the number of instances are, let's say 5K. And then in this, let's say there are only 7K. So now it's very obvious that you can probably give more weightage to this local site, because it is learning parameter on 10,000 data instances. Okay. For example, while this this local copy of the model actually learning patterns only from 2K instances. So which means it is only contributing 1/5 of what this node is contributing towards model update. Okay. So that since it is learning from more data, probably that must be given more weightage compared to rest of the other participating sites. So it is just about number of data points. There could be other factors as well. For example, even you can even break down this problem into number of features that are being utilized at different local sites. Okay, all such various other data related characteristics can also be brought in here. Accordingly, you can assign some weighting scheme. Okay, otherwise in the standard averaging mechanism, average way of aggregating model weights from local copies, we just simply go with a kind of equal weighting, right? If there are 4 participating entities, then weightage for each of the updates coming from local model are going to be simply 1 out of 4. Okay, 1/4. Because when we divide 4 into 4 parts, then probably each node will have weightage of probably 1/4, right? So it's kind of equal averaging, right? Equal weighted averaging. Or you can also even go for kind of specific weighted averaging as well. Okay. Besides this, we have many other choices for aggregation. And once the aggregation is done, then in the second step, now at the end of this, what has happened is just one iteration is completed. One iteration is completed. Now for the next iteration, the global model is expected to share the updated global model copy with all the local sites. And now all the local sites will receive the parameter that was aggregated by the global model. So now what actually happens here, because of this, we get one important benefit, that is now every local copy has some knowledge about data patterns that are learned by other local sites, because now for the next iteration, local site 1 actually gets the global model copy again in the global model, which is updated by aggregating all the local updates happened in the previous iteration. Okay? So that now the knowledge exchange between or across these local sites are also happening with the help of the central server. Okay, so that now from this, then again local training will take place. As usual, the loss will be estimated, and then the gradient update is going to be shared with the central server. Similarly, this again aggregation will take place and so on. Okay, this will be repeatedly happening for how many number of rounds that you wanted to basically run in order to learn right set of parameters for the global model. Okay? So this is what actually mentioned here in this simple procedure. So in each round of training, so each local device actually downloads the initial global model from local server, and then local device trains a local model on its local copy of data, and then only the local models are sent to the central server after no only the local model. I mean the parameter update, no, which means that theta, right? That sorry, the delta W, theta T, right? Only the derivative, the derivative of the gradient loss is what actually sent to the central server, and then central server performs the normal averaging or fair averaging or even weighted averaging of all the local models that it has received in order to update the next global model for the next iteration or the next round of the federated learning. Okay, so then the server sends the new global model back to all the participating devices, and then once again, local copies will pass through all the data instances, all the training instances that they have locally available to it, and then again it will recommend model. It will recommend gradient loss with the server, and then server again with the with an averaging mechanism or the aggregation mechanism. It will again consolidate them into a single global model, updated global model, and then again that will be shared, and then this cycle will continue no, until we figure out the right set of parameters for the global model, consulting all the data instances which are present across various local sites. So that is basically the overall idea of the federated learning. So there's one more example here, the same thing, but explained in a different way. Let's say, so start with the same initial random global model on all the edges. Edges, I mean edge devices. Okay? We can think of these edge devices as kind of local, no, very resource constrained devices. Like maybe all these edge devices, maybe like mobile phones, or all these edge devices, maybe like kind of sensor or CCTV camera or any sort of camera module or kind of AI vision camera module, and or any other edge accelerator device and so on. Okay. And then yes, the one more important step that it does is selecting the subset of clients, and that process is also called as client selection. Let's say there are 4 edge clients which are participating in the learning process. Okay, so not necessarily the global server or the central server should accept update from all the clients which are in the maintaining its local copy. Right? So for example, at every step in the learning process, central server has the privilege to choose, let's say, any 2 out of all the available local sites, or any 2 local sites which are responding first. Okay, many client selection criteria could also be defined, for instance. Okay, or any top 3 no, quickly responding local sites could be considered, let's say, for this particular round of training. Maybe for the next round of training, maybe the other 3 may get the priority to participate and so on. Okay, but all the local sites will be equally participating, but they will be contributing to different training steps in the overall learning process. Okay, that could be an idea. Okay, with which what we can basically do, so central server need not wait, till it receives updates from all the local copies. So that eventually the time spent on training will also be less, because it need not wait no, till it receives model updates from all the local copies, right? It just waits only for 2 quick responses that are coming from any of the available edge devices, edge clients. Okay, so that is the idea here about client selection. and then perform the forward pass much like any other standard neural network training. And that is what actually happens here, right? So you identify some, yes, of course, you go with a mini batch kind of update. You don't update your parameters based on looking at every data instance. Okay, there are many various ways you can actually do the model update locally here. So one is mini batch. Mini batch is one. The other one is simply the batch, which means you use your entire training instance. You use your entire training set. Entire training set is going to be used as a single batch, so that after go through all the instances in the training set, finally one update will take place. But in case of mini batch, you can define, let's say, the mini batch of, let's say, 32 or 64 or 128. Okay? So which means if you have, let's say, 10,000 instances in your training set, and wait update going to takes place locally, consulting every mini batch. Okay. For example, now how many times the model weight locally will be updated? Model weight will be updated locally. How many times? It is going to be simply 10,000 divided by the size of the batch size, 32. Okay. So these many updates are going to take locally, and the final updated local final updated parameter values are then going to be shared with the local central server. Okay, that depends on the size of the number of batches, and then those many updates will take place. So in case you go with, let's say, a stochastic way of doing it, okay, in case you go with a stochastic way of allowing model update to take place locally, what would happen? Stochastic in the sense the denominator of this will be simply 1, so that every point when it is consulted by the model, there will be a model update. Okay, but this is something that is not generally recommended because it is going to incur a huge computational overhead. But generally suggested is not even to go with entire training set, no, consulting entire training set and then going for just one update again is not a good idea. It is better always to try out some mini batch way of doing it, and we can again, the size of the mini batch is again again a hyperparameter which you can decide based on the number of instances you have, number of and then the complexity of model you have. Now, accordingly, you can fine tune an ideal or the most relevant value for the size of the mini batch. Okay, right. So that is what basically happens at every local copy, and then the central server will appropriately be updated. Okay, so and then there are slides here following, showing every step one after the other. Then we apply the gradients to the local model, right? So the gradient, this gradient is something that we have initially received from the central server, and then the different local models are basically trained on each edge device using the local copy that it has received from the central server. Okay, so this gradient is something initialized by the central server. Okay, for the first step. For the subsequent step, yes, again the aggregated weights of the parameters will be shared by the central server. Okay, that will then will be used for local training, and then it goes through the forward pass over the data in the previous step, and then once the gradient is estimated, and this gradient will flow back towards backward of the model. This is what happens in the usual neural network training. Right? That is what we have seen in the very first, at the start of the presentation. We have looked at the way how the entire end-to-end machine learning pipeline works. Okay, and we have observed that the learning algorithm module is actually running in an iterative manner. Right. So that is what happens here. So it depends on the number of batches you have done, and the multiple steps will be performed here in order to update. Okay, so how many times this iteration will take place, and that is where we see the difference between epoch versus iterations. So let's say you run just one epoch at every local site, but since you have decided, let's say 128 as your batch size, the number of not iterations basically, iterations and epochs can be interchangeably used, but here it is not iteration, it is basically the steps. Okay, in order to complete one iteration or one epoch, how many steps of operations are to be done? It is going to be 10K divided by the total number of training instances we have divided by the size of the mini batch. Okay? So these many steps. So at the end of every step, weight update will take place. Okay, this will repeat these many times. Okay, this loop will repeat these many times. And finally, whatever whatever change is recommended by the local copy will be shared with the central server. Okay, so now the gradient is obtained, and the gradient will flow back, and then in order to tweak the parameters of the local copy, okay, parameters of the local model. This will done until we process all the instances in the training set, and then finally we recommend, okay, this is the best possible, this is the gradient loss that we have assessed, and then that information, that gradient associated to all the weights involved in the local model will be shared with the central server for aggregation. And then, yes, so this happens on all the local copies. And then after a fixed number of epochs, I mean one epoch in the federated machine learning setting is the central server shares the parameters with the local model, initial parameters with the local model, and then local model updates central server with the updated parameters that it has learned from the local copy. And that includes, and that should be received from all the local copies or whatsoever clients which has been chosen for the current iteration. Okay, that put together involves one epoch, and then how many times that we do this loop. Okay? So global model shares the copy of parameters with the local models, and then finally all the local models update or respond to the central server with updated parameters that it has learned from the local copy. But this put together involves one epoch. Okay, one epoch. And besides that, depends on the type of mini batch you use, the number of mini batches you use, the number of steps will also be iterated inside. Okay, so this is something that we see in the classic neural network training. Especially the number of epochs here in this case talks about this loop, this training loop, okay, involving central server as well as all the local site devices running in local sites. Yeah, once at the end of the epoch and all the local copies are updated to the central server then aggregates the model, and then it will again sends back the updated model to all the local systems. Again, all the local systems will also update the central server after the local training is done. Okay, this entire thing will be continuing for several iterations till the convergence, or you can have a fixed number of epochs. Let's say you have decided number of epochs to run, let's say 100 or 200 or 300, 500. Okay, so till that time, this training loop will continue. And then finally, whatever model parameters that central server aggregate from all the clients at the end of the epoch is what your original model. Okay? So now that model actually is a model that is learned in a distributed manner on data located distributedly across various local sites. So that's the overall idea of the federated learning process. Okay, again, the same thing is repeated here. I think some of them are self-explanatory, and which you can actually go through yourselves. So whatever we have seen, the major steps involved in the training pipeline, right? Only the training, which means only wherever training is involved, right? These steps which are marked in green color here, they are all where actually the training begins. Most importantly, this is where training happens, right? Because training requires data, right? These are probably kind of data exchange. So kind of data gets transferred from server to client, and then here again there is a transfer of data happening from client to server. But the actual training is basically happening here. Okay, this is the training loop. So these are the algorithms involved in training. Here is the averaging, the aggregating model weights that the central server has received from local copies. So they are basically averaged, right? It is also known as Fed average. So it is also called as Fed average, and this is a very classic way of aggregating model parameters from local copy. So here is the algorithm to do so. So the first algorithm says that we initialize theta 0, and then it is actually spread across all the clients. Okay. And then for each client, and we get the model update, and then and then finally we update the parameter, and this is just the gradient. GT for k is the gradient, and then this theta t is the gradient. And the gradient is actually this is the standard parameter update rule, right? A standard gradient descent parameter update rule. Right. So this is the old parameter, the parameter obtained in the previous timestamp, that is t minus 1. The current, the parameter for the current timestamp, theta t, is actually updated with the old value of weight, and then minus, and then this eta. Eta is your learning rate. This is a standard gradient descent update rule. Okay, this is the rule that we use. And then based on the way how this gradient was calculated, and the gradient is now used here, multiplied by the learning rate, so that we don't want to have as we all know, the learning rate is expected to be small, right? Because we wanted to learn gradually but smoothly. That is important. So at the end of the iteration, when you plot the loss curve, right? When you plot the loss curve, so it is expected to actually decrease over epoch. Okay, we want this function to be smooth. Okay, we want this function to be smooth, but it is not expected something of this kind. But this is something which is not preferred. Let's say, okay, in case if this is your training curve or the loss curve, see, now the loss is not smooth and it is not stable, right? So this is more stable. The green curve is very stable compared to the red curve. Red curve is having a lot of spike here, which means training is actually fluctuating, right? So you are not able to go in a proper direction so as to update the gradient, update the weights. So that is the challenge we face here. And then in federated learning side, yes, we choose the clients. So we choose the clients, and then based on those clients which are chosen at this particular iteration, then the model weights are going to be aggregated. So based on average, so we are just simply dividing it by n. That is probably the number of clients which are participating in contributing weight updates to the model, global model. So this way, the way how client updates takes is something like this. So this is the standard the gradient descent rule again used here, just to show you the basic skeleton of the algorithm. So this was a big proposal when it was published in 2019 in this particular paper. Maybe if you need more details about this algorithm, a very classic algorithm. Probably when you work with federated learning algorithms, probably this is something that would be your baseline model. Okay, and whatever you contribute, probably that is expected to outperform this basic implementation of federated learning training algorithm. Right. Again, federated learning is seen in multiple settings. Like one is called cross-device federated learning, and another one is cross silo federated learning. Okay? So there is a characteristic comparison seen here in this slide. So in case of cross-device federated learning, where mostly you find a lot of research papers on cross-device federated learning, where they simulate the number of devices using some sort of simulator, and then they run some federated learning algorithm on top of it, and then report results. So where the number of participating clients are going to be in millions in number. Okay? So the number of clients participating in running federated learning are basically a kind of lightweight devices. The devices are very lightweight, like IoT devices, mobile devices, or any other edge devices, so that it will have very less compute capability, right? So while the cross silo federated learning involves a very small number of institutions like hospitals, data from different hospitals are the participating entities, or banks, or participating entities, or insurance companies are participating entities. So we don't have hospitals in millions in count, right? We do have reasonably hospitals in probably 10 to 100 or 10 to 1000 no, in any practical applications. Again, banks are again not in numbers of thousand, right? Banks are again in numbers of, I'm talking about nationalized banks, which are not in some number beyond 100. Okay. And since these domains are very sensitive, unlike IoT devices are kind of irreliable devices, right? They are not reliable, they are unreliable devices, and it can be harmed because of some external factors, right? It can probably malfunction at any point in time, right? And they are very prone to attack. Anyone can easily attack IoT devices, and then attacker can make it go wrong and then malfunction, right? But on the other hand, the hospital systems, the databases that they maintain at hospital, and the banking data, transaction data that are kept at bank are very highly secure. Okay, highly secure, and moreover, the compute capability that they have are very high, while the compute capability we have with this cross-device setting are very low. And then the nodes, the participating nodes in this cross-silo federated learning are very stable, because they are used in very critical applications like critical domains like hospital and bank, and they have very stable nodes. All the participating nodes in their compute grid or storage grid are going to be very stable and very reliable. And moreover, those servers are always available, so it will never ever go down. It will always be available 24/7. But these IoT devices are not so. Maybe if IoT devices are configured in a manner that it can operate only at the temperature of, let's say, 25 degrees. Suddenly, when temperature goes below 25 degrees, then IoT device will then start malfunctioning, or it will go down quickly. They are not so stable. Okay. So I hope you now see, based on a kind of client participation, so the entire federated learning architecture itself gets a different image. And then again, IoT devices will generate or collect only data with small in size, and then data are going to be heterogeneous in nature. And then there is some statistical property that we observe in the case of federated learning is that non-IID. Okay? So independent and identically distributed. It is a property that we see in statistics, right? I'll talk about that. Then coming to so basically it is non-IID in the case of cross-device setting, and in case of cross-silo setting, it is IID, which means it is going to be independent and identically distributed, which means see, every data instance will have some associated label Y, and the next data instance will also have, let's say, same set of features as that of X1. This X2 is independent of the previous one, because the outcome label of X2 is independent of the previous one, right? For example, I have an image here where I have an apple, and then the label associated to it is, let's say, A, apple. It indicates that it is an apple. The second image has, let's say, orange, and the label assigned to it is orange. The prediction of this image does not have any dependence on the previous instance, right? That is what I mean to say. That is one of the properties of IID. Right? Besides that, the way how we distribute data across local sites. For example, it is a binary class classification problem where we have, let's say, 1,000 images, 500 of them contains apple in it, and 500 of those images contain orange in it. Right? Now you are actually, let's say, distributing these images in order to simulate the federated learning setting. Let's say you have two nodes in the federated learning. You have local copy L1 and then L2. Now you decided to, let's say, distribute 500 images each to two local copies. So now this receives 500 copies, 500 images, and this receives 500 images. Let's say this 500 images, let's say, contains 250 images of apple and 250 images of orange. And this 500 again receives 250 images of apple and then 250 images of orange. Right? So now here we are actually identically distributing data instances carrying different labels. Okay, so it is not that you assign, let's say, 350 images of apple to this local site and then only 150 images of apple to this site. If you do so, it becomes non-identical. Okay, so this is an example for non-IID. If it is IID, then it should be preserved at the class distribution should be fair across the local participating nodes. I hope this is clear, right? So mostly in case of hospital and banking domain, data instances are going to be IID in nature because the fixed number of features are going to be used to describe hospital data. Fixed number of features are going to be used to. When I say features, I mean the columns, right? X1, X2, X3, and so on and so forth. X2, Xn. So I mean this as columns, right? Which means the features. So the features are going to be very stable across various hospitals, right? Every hospital will initially have the triage unit, right, where they will take the vitals first, right? Probably every patient visiting hospital, the blood glucose will be assessed, and then pulse will be assessed, and then heartbeat will be assessed, and so on, right? Heartbeat, pulse will be assessed, and these are some of the pressure will be assessed. So that is what actually happens at every hospital. So it doesn't differ from hospital to hospital. So that's why mostly we will be dealing with IID kind of data distribution when it comes to cross silos, and we'll be dealing with non-IID kind of data when it comes to cross-device federated learning. Okay, so according to this, again, the entire architecture also differs. Okay, and again, yes, compute is going to be less high in case of cross silos and will be less in case of cross-device federated setting. And then the preferred models are typically lightweight, as we are dealing with lightweight devices. So we cannot run heavy AI models or heavy machine learning models on top of these mobile or IoT devices. Okay, but we have powerful computers, we have powerful, stable, always available servers in case of cross silo setting. So we have no restrictions and we can have large and very complex models. Okay? And then so these are the key challenges we have, and then it leads to communication overhead, and then the fault tolerance, because the participating clients are not tolerant enough, right? So they can quickly, they have no fault tolerance. And then again, what basis will you choose clients, and what is the dropout factor? And then we need to deal with heterogeneity, and it doesn't scale well because they are very lightweight devices and it cannot scale well. But on the other hand, in cross silos federated learning setting, so you have very trustworthy infrastructure available for you, so that it will be fault tolerant. And of course, it will have communication overhead, but it will gracefully handle it because of the available resources and available resources, which means stability, and then the security at which the level of security that these infrastructure gets is very, very high when compared to the IoT kind of device clusters. And then aggregations are of two types, basically synchronous and asynchronous. So synchronous in the sense, since all the participating nodes, like hospitals, let's say 100 hospitals. So all the hospitals will have almost same schema, right? When it comes to storing data. And then even there will be some homogeneity seen in the hospital infrastructure. Okay, the computing infrastructure or the storage infrastructure that hospitals maintains will have a kind of standard protocol. There could be minor differences, but hospital to hospital, but not much. Okay, but in case of IoT, it is not so. In case of cross-device setting, it is not so. There will be a huge variation, and that leads to high level of heterogeneity. It's a big challenge for cross-device federated. So where in case of cross silo setting, and we need to just deal with only a homogeneous collection of nodes, and then even data are homogeneous, infrastructure is homogeneous, and thus we don't have this as a problem. Okay? It's very easy to deal with. Right? So asynchronous, aggregation is going to be happening in an asynchronous or partially synchronous mode, while in cross silo setting, the aggregation will happen in a synchronous mode. Synchronous mode in the sense all the clients will participate, and moreover, only when server receives updates from all the clients, then only the aggregation will be performed, and that is synchronous. which means server will wait for all the participating clients to submit their updates. Okay, that it has the updates on weights that it has learned from the local copy. But in case of IoT devices, as they are not stable and then so reliable devices, they are not so reliable. So it is not a good idea to wait. No, server is waiting no to receive updates from all the participating IoT devices. Okay, it not necessarily. So whenever update comes from any of the clients, and immediately you go ahead with aggregation. So don't wait for rest of the clients to even respond. Okay, whoever sending updates first, just immediately apply them through some aggregation protocol, and then you update your global model. And then immediately don't wait for all the remaining clients to respond with their updates, local updates. You before that simply broadcast the updated model with all the other clients which are actively, seamlessly working with the server. So that is what synchronous and asynchronous. And I have a separate slide to explain, this asynchronous and then synchronous aggregation. When it comes, we will discuss in detail. So basically, in case you work on federated learning, and you would be either working on cross-device federated learning or in the cross-silos federated learning. Maybe if you take up a research problem and to address it through federated learning, as the case may be, right? It is not as the case may be. So in case your data are like this, your data follows IID, no, your data follows this IID principle, or your data, or you have distributed data which all have same set of features, and then the participating nodes are actually homogeneous. So then what you are actually doing is a cross silo federated learning. And on the other hand, when you are working with learning from or learning in IoT devices itself, or in mobile devices itself, or in the mix of IoT devices, mobile devices, and then some sensors, and then some camera module, and then some vision sensors, and so on and so forth, like thermal cameras, and so on and so forth. When you try to learn from such a mix of heterogeneous data collection, moving with heterogeneous collection of client nodes, then actually you are working with cross-device federated learning. Okay, so any federated learning work you identify from literature, and you can put it into one of these two buckets for sure. Okay, yeah. So it is now 3:24. I'll probably stop here, and then I can cover the rest of the things along with aggregation strategies or advanced aggregation strategies we have in the context of federated learning in my next talk on 8th of May.
Yes,
So meantime, I would be happy to take up questions from the participants if you
yes,
have any.
yes, sir. Thank you, sir. Thank you for your very informative presentation, sir. Now we will open the floor for queries from participants. Yeah, dear participants, if you have any doubts or any questions or clarifications, please unmute yourself and ask. Feel free to raise your queries. Please, Sir is here. Any queries from participants, sir? Any queries?
I was talking to you
Yeah.
earlier on.
Yes, sir.
Yeah,
Yes, sir.
please,
Please
please,
welcome,
sir.
sir. Yes,
Please
sir.
go
Yes,
ahead.
sir.
Yeah.
Yes, sir.
So basically, we are doing a research on, using federated learning, sir.
Okay.
And I was telling to you that your input has given me some thoughts to go
Okay.
in different direction as well.
Okay.
We are basically doing a research on organ transplantation, sir.
Okay.
Organ transplantation, where we have taken data set from United Nations organ sharing agencies, sir.
Okay.
UNOS data set.
Okay.
And we are trying to do with blockchain and also deep serve technology framework, sir.
Okay.
Because
So can you?
this one is a
Yeah.
very
Yeah. Go ahead, please. Go
because
ahead, please.
because organ transplantation research basically is a very serious thing, and also it has got different laws between countries which are while sharing the data. So we have communicated with the UNOS for almost 3 to 4 months to get the data itself,
Okay.
and now we are working on it. But
Can you
what
throw some
today's
light on?
session?
Yeah. Please go ahead. Yeah.
What today's session from your end gave us a different thought, because you were talking about different types of federated learning, which we did not focus earlier on.
Okay.
And now we can also think on that direction. So that's one thing which we have taken from your session today, sir. Thank you very
Okay.
much for that.
Thank you. Thank you.
Okay.
And it's not more like a question answering, it was like a kind of
Yeah.
feedback I think I
Yes,
received.
sir. Thank you,
Grateful.
sir. Yes, sir. Thank you for your explanation, sir. So once again, I thank you, sir. On behalf of our institution, I sincerely thank you, sir, for this insightful session on foundations of distributed and federated learning under quantum faculty development program, sir. So your clean explanation of key concepts and their real-world applications made this session highly informative and engaging, sir. Your expertise in computer vision, natural language processing, and lightweight AI solutions was clearly reflected in your presentation, inspiring all of us to explore this domain further. The knowledge and perspectives you shared today have greatly enhanced our understanding of this emerging research area. Your valuable time, effort, and willingness to share your expertise are deeply appreciated, sir. I'm confident that this session has been highly beneficial for all participants and will motivate us in our academic and also in our research activities, sir. Once again, we extend our heartfelt gratitude for your valuable presence and contribution, sir. Thank you, sir, for making this session a memorable and enriching learning experience. Thank you so much, sir.
So thank you so much for having me here, and
Yes,
let us meet again on 8th.
Yes, sir.
And
Yes,
see
sir.
you back
Definitely,
there on
sir.
8th.
Yes, sir. Yes, sir. Definitely, sir. Yeah, thank you so much, sir. Thank you
Thank you
very
so much.
much.
Thank you.
Yeah.
Thank you,
Yeah,
everyone.
thanks.
Thank you.
Dear participants, with this today's our program concludes. I thank you for your valuable participation and support. I kindly request everyone to rejoin tomorrow using the same meeting link by 8:50 a.m. since because the session will commence promptly at 9 a.m. Thank you so much. Please kindly may leave the meeting now. Yeah. Thank you so much.
Madam, what about the feedback link for today's session on the
So already
curriculum?
we have posted in chat box, sir.
Okay,
Already
then.
we have posted, sir.
Okay.
Yes, sir. I kindly request every participant to submit that feedback form for both attendance and feedback, please. Already we have posted in chat box. Once you have submitted means you can kindly leave the meeting. Thank you so much for your participation. Dear participants, we have already posted the feedback link in chat box. Once you have submitted means you can kindly leave the meeting. Thank you so much. Dear participants, once again I repeat, we have posted our feedback link in chat box. Kindly submit that form. Once you have submitted means you can kindly leave the meeting.